Thank you, Gary. Thank you for the very kind invitation to join you today. I was struggling on what I should try to cover during the day. I have to say that I believe that I know next to nothing about any discipline that you can think of, but there are a few exceptions. So endodontics is one such exception, and I know absolutely nothing about endodontics. So not just next to nothing, but absolutely nothing. So hopefully that will not create a major communication problem, but I have prepared some slides to share with you. I wouldn't like that to end up being just a series of lectures. I would like you to participate, interact, question, disrupt, tell me that I'm completely wrong in what I'm trying to tell you. So these are some disclaimers to start with. This is not an objective systematic course. There's not going to be a single systematic review that you will see here, although there will be some bits and pieces of evidence that come from systematic reviews. Now, to take one step back, how many people in the audience have read at least one systematic review in their lives? Okay, very reassuring. Have read one systematic review that they felt that there was no concern, they could take it at face value? Almost nobody. Okay, well, one, maybe. How many people have published a peer-reviewed study? About half of the audience, okay? And how many people felt that that peer-reviewed study, or at least one of the multiple peer-reviewed studies that they published, had no major problems? Okay, one, again. Can you give me a quote of that study? Because I haven't seen a single study that qualifies for that, including all of my own. I mean, I think all of my studies have tons of problems. So the choice of subjects is subjective and not based on systematic reviews. I'm probably very biased, and in some questions I'm terribly biased. I suspect that, but I'm struggling to prove that to myself. There may be tons of errors in what I believe in and what I will try to discuss. So watch out for errors. Don't necessarily follow me. Think, tell me that I'm wrong. If you don't do that, then I will really feel very bad. So here's a few examples of some errors that I have made in my career. I've made probably millions of errors, but I have selected a few of them related to research, obviously. This is my first peer-reviewed paper, a case report that took 84 pages to write and trying to explain more than any theory of everything. I was a resident at that time. I had seen a patient who had a very interesting combination of things that were happening to him, and I thought I should write a case report. So that case report took 84 pages, and I shared it with the physician-in-chief, and what would you do if you got a case report of 84 pages? Publish it as is. Okay. So he did review it, and he sent me some comments, and I tried to publish it, and eventually it ended up being a case report published as a letter to the editor. So why am I saying this? Because we just try to do too much, and we think that we can explain everything. But it doesn't work necessarily that way. So we think that our theories could explain a lot, but that's not necessarily the case. True story number 2. Again, this is one of my early papers. I was running some calculations on a mathematical model, and the model predicts that you can live for 800 years. This is actually a mathematical model that I was doing for HIV-infected patients. with advanced disease and with end-stage multiple clinical problems. Was it correct? What do you think? Probably not. So I was looking at that, and I have to tell you that the one thing that I'm very proud about in my life is that in my early years I participated in that wonderful collaborative effort trying to develop new treatments for HIV. Can we have a little bit more light? It's getting a little dark, you know, early in the morning. Some people may sleep. I don't know. I think that one of the major advances in medicine is that we've managed to find effective treatments for that disease. So now people can live practically normal lifespan lives while it used to be a deadly disease. And clearly, though, that would not be 800 years. And actually, the model predicted that even without therapy. So some people in my team that I showed these calculations said, well, if this is true, everybody should be infected with HIV so that they can become immortal. And I just had to go back and retract all my calculations, and I saw that a plus sign had become a minus sign. And that caused all the disaster. So whenever you have a research finding in your own research or in a paper that you're reading, you have to ask yourself, how reasonable is that finding? Sometimes we see lots of findings that don't really make sense. It's just an issue of common sense. It's not difficult, complicated statistics. It's just common sense that if you think that about someone living for 800 years, this really cannot happen. Is that a common problem? In your experience, have you come across this type of mistakes or errors? All the time. All the time, yeah? Does someone disagree with that? In my experience, I see that every day. Every day I make quote-unquote discoveries in my data and analysis that if they were true, you know, my team would have received 50 Nobel Prizes. But it's just very common. And some of that actually may spill over to the peer-reviewed literature. You know, obviously, we found the error and we didn't submit that. When we corrected the calculation, it was not 800 years, it was 0.8 years. And that was publishable. But you will see lots of papers that are equivalent to what I'm describing to you now, that just have absolutely no link to common sense. True story number 3, refutation under the best circumstances. In 2004, I was a co-author on a paper that was published in the Annals of Neurology with the title, UCHL1 is a Parkinson's disease susceptibility gene. And a year later, actually a year and a half, I think it was February of 2006, there was another paper published in the same journal, highest impact factor journal in neurology. UCHL1 is not a Parkinson's disease susceptibility gene. In the paper that was my team's, it was one of my best papers by far. It was really wonderful. I had the best colleagues from the best institutions, the best methodologists, the best clinicians, the best epidemiologists. Our design was impeccable. Our methods were crisp and accurate and efficient. It was a worldwide collaboration. All the teams around the world working on that topic at that time, joined forces. And we got a very nice result. The paper was, I'm telling you, one of my best, maybe my best. And then within 1 year or a year and a half, you have another team publishing in the same journal with about triple the sample size compared to what we had accumulated, a result that is completely the opposite. What do you think? Who was correct? The larger sample size. So I think that they were correct, yeah. And what did we do wrong? I think we did nothing wrong there. We really did our best. We spent about 4 years trying to work on this. We had more than a dozen scientists working in 6 different institutions around the world, and lots of other scientists contributing data from around the world. But it just happens that sometimes, even under the best circumstances, you will get a result that will not hold the test of time. And there will be larger studies that will come forth, and they will show that that was not correct. Now, it's interesting. That particular topic then, there was another team that took both papers, both data sets, and anything else that had been published. They performed a meta-analysis. It was published in the American Journal of Epidemiology, which is like the premier or a premier epidemiology journal. And what do you think that they found? What would be your guess? Well, actually, they validated our study. I knew you would right all the time. Of course. And then we said, well, we need to settle that. So we created an even larger consortium, and we had a sample size of 10 times the original study. And what we found is that there's absolutely no effect of UCHL1. Now, we've had a hard time to publish that. Nobody wants to see that published. If you read the literature, the latest update, the evidence-based update, would suggest that UCHL1 is a Parkinson's disease susceptibility gene. Now, those who are insiders know that this is not the case. But can you be insiders on every tiny bit of scientific field or literature that is out there among the 22 million papers that appear in PubMed alone, and probably far more in other databases? So you need to be very careful about taking the literature at face value, even when the studies seem to be very well done.
Why wouldn't the journal want to publish something that corrected a widely held error?
Yeah, considered to be low priority. So I think it will get published. I have no doubt about that. But sometimes negative results don't really attract the attention that they should attract, or at least the approval of getting published.
So is there other research going on now based on this incorrect finding? Are they testing drugs to try to...
Not necessarily drugs, but I'm sure that some labs would be pursuing that line of research, maybe unaware of what has happened. So a wrong finding could really be a nidus for building a much larger story and invest a lot of research for the wrong reason. So this is a big problem. So this is the plan of what I was thinking to do. Obviously, there will be lectures, but I'm struggling to see how we could have less of lecturing. Gary tried to send me some research articles in endodontics so that I can become a little bit aware of where I am and what's happening. And I would be very glad if you wish to discuss some of these papers with you, or actually it would be even best if you could discuss those and we could have them on the screen and people could comment on those and I can tell you what I think. I would like to have quite a bit of brainstorming on research and meta-research questions. So you have a wonderful consortium in place, and this gives you a lot of power to do some very interesting research as a group. And I see that you already have a wonderful tradition of using that resource to conduct research. I understand you have a randomized trial on 1 versus 2 visits that you've been working on. We can think about ideas, brainstorming on design issues and methods and ideas that would be interesting in your field. Again, I know absolutely nothing other than the few papers that Gary sent me. But it would be nice to discuss some issues in light of what I'm going to show you. And I would like also to have an impromptu component. So if people have some ideas of how we could make that more exciting and interesting, please do let me know. In terms of the lectures, I don't think that we will have time to go through all 5 modules that I have here. If we do that, probably the course will have failed, because probably I will just be talking and talking and talking. I would like to go through at least the first 2, which is significance and credibility of research findings and biases and errors. If we have time, it would be nice to delve a little bit in translation and reproducible research. And if we have time, maybe a few things from quality of the evidence and heterogeneity. I doubt we will have time for geometry of the evidence, but I have all these slides here so that if questions arise, we could try to discuss them. So significance and credibility are 2 different things. This is one example of why they're different. Does diet cause cancer? What would you think? How many people would say, yes, it does? But if we just keep it at a black and white. Yes versus no. Yes. Yes. No. Okay, so mixed feelings in the audience. So this is not a scientific question, or it could be a scientific question. We decided to look at a cookbook, not the scientific literature. So we took the Boston Cookbook. It has been out there since the late 19th century, and had many editions. It's very popular and widely used. We randomly checked 50 ingredients. And how do we do that? We use a pseudo-random number generator. The computer will select the pages and the recipes, and then we take randomly ingredients for those. How many of those are associated with increased or decreased cancer risk if you go to the scientific literature? All of them. All of them, okay. Peer-reviewed scientific literature. The best possible evidence in science, in a way. Any other thoughts? All of them is one option?
What you did was, you filled the filling that you know that he probably would do a lousy job at, because the patient was there, they were already done crying, you could just do it, just take care of it, and you were going to suffer what was going to happen afterwards.
The patient was a friend of my family personally, so I did it in an effort to try and educate him
Okay.
on alternate technique.
Right.
Right. I have a slide that's going to help you today. I do have a slide that's going to
So is everybody as skeptical? Okay. So this is interesting. I think you're more skeptical than I am, because for example, I do believe that bacon does increase the risk of cancer. Nevertheless, I had bacon this morning. I mean, Gary can testify that. You know, maybe I'm a little bit suicidal at times, or.
Dad, you can die now. I had bacon too.
Okay, so this is the literature. There's 40 out of 50, and the list is very long. Now, how about the other 10? There's things like vanilla that are not in the list, but actually, if you look for vanillin, then it would be in the list. So the way that we searched was to look for the ingredient. I mean, if you go down the path of biochemistry, you will see probably more happening. But at least 40 of them had some literature, scientific literature, peer-reviewed literature, that they increase or decrease cancer risk. Now, this is it's not an apples and oranges meta-analysis. It's a wine, tomato, tea, sugar, salt, potato, pork, blah, blah, blah meta-analysis. And I have plotted for you the effect sizes, a relative risk, which is how many times the risk of cancer goes up or down with one more serving per day of each one of these ingredients for different types of cancer. So the top half is different cancer types, and the bottom is different types of ingredients like wine, tomatoes, tea, sugar, and so forth. What would you think would be reasonable relative risk based on common sense? Let's forget about statistics and think about common sense. Now, if you all believe that none of that should have any effect, you're telling me that the relative risk is going to be 1. 0 on a log scale, or relative risk of 1, meaning that the risk is exactly the same for cancer on those who have more or less of that food. But if you were willing to believe that there is some association, let's say, between bacon and cancer risk, or between red processed meat or fruits and vegetables, what kind of relative risk would make sense? I'm coming back to the 800 years life expectancy situation.
Especially for
Yep.
your subset. You guys aren't used to this. You're used to doing great work based on the fact that you understand the periodic table of elements, you understand science, you study very hard, and this type of interaction you're not used to.
Yeah, so it's a relative risk, which means that if you were to have 100 cancer cases, if the relative risk is 0.5, with one more anything, it would go down to 50 cancer cases.
This microphone over there. Okay? Keep coming down the line. There we go. Go ahead. We're gonna.
You skipping me?
I'm sorry.
You want a female or do you want a...
No, let's go ahead. Go ahead, please.
My name is Tim McManus. I'm from Windsor, Ontario. You know where Windsor is?
Get out of here.
By the end of our meeting, I will become a stronger communicator.
So this is a decision-making issue. I mean, you know, once we know what that risk is, we can decide what we want to do, and how strongly we should try to implement some policy changes or individual choices. But I'm trying to focus as a start on what would be reasonable relative risks. So if you're willing to consider that there may be some increase or decrease, and you want to move away from 1.00, where would you go? Would you go to a 0.5 or a 2, for 0.5 for a protective food and 2 for a food that increases risk? And if you go to 2, it means that with 1 more serving a day, the risk of cancer in the world would double. We have double the number of cancer cases. And with 0.5, it means that with 1 more serving a day, we would have half of the cancer burden in our population. If that were the case, it would have been very easy to almost get rid of cancer. You know, you would just give 1 more serving of fruit and 1 more serving of vegetables, and cut back a little bit on salt and cut back on red processed meat, and cancer would go away. So this is not likely to be true, even if we do see such results. And actually, as I show you here, we do see such results published in the literature. We see tons of results with relative risk of 0.5 or less, or 2 or more, which are not commensurate with just common sense, with expectation of what might be happening. Now, here's the results of the 10 most recent studies on these food ingredients in terms of the standardized Z-scores. What is a standardized Z-score?
Okay.
Yeah.
We went on for steak. Okay, so now I want to know, last time you were talking a lesson, and you felt you were making a good case for whatever, and it didn't go your way.
I'm considering relocating the office.
Okay?
She doesn't seem to be an active participant.
Right. So there's tons of such studies, and we will discuss some of these biases in the second module, but since you touched on that, there's clearly a recall bias, and this could operate in different ways. It could operate if you know that someone developed cancer, then if you ask what you have been eating, maybe they will remember that they were eating quote-unquote unhealthy foods, and this is why now I develop cancer. So it's a self-fulfilling prophecy acting retroactively, in a sense. So in that case, the bias would cause stronger associations compared to what they really are. But if you just ask people to remember what they ate and you don't have the outcome yet, as you say, they will not really remember what they're eating. So the measurement will be noisy, and if there's no bias to link it to a known outcome, the result will be that, on average, the strength of the association will be diluted, because we're not measuring very accurately what we're supposed to measure. People who were having tons of bacon would not remember that they did that, and people who had no bacon, maybe they will think, well, yeah, I did have some, and therefore, with noisy measurement, with this type of misclassification error, the relative risk that we will get from the study will be smaller, actually, compared to what the reality is. So we'll come back to that, but are you familiar with what a z-score is? You're familiar with the normal distribution, isn't it? The bell-shaped distribution. So a z-score is where exactly on the horizontal line we are on that normal distribution. So a z-score of minus 1.96 or 1.96 corresponds to a p-value of 0.05. It means that we have 2.5% on each side of that normal distribution that we are lucky or unlucky to find ourselves. So the green color here are the main results of these studies. How would you describe the main results of the single studies? This is the left panel. What type of distribution of z-scores do you see? They're significant. So almost all the p-values in these papers are nominally statistically significant. They correspond to z-scores of either less than -2 or more than 2, which means a p-value of less than 0.05. And there is a big missing gap in the middle. Now, what would you expect for the distribution of these p-values if you are correct that none of these food ingredients have any association with cancer? It would be mostly points in the middle, because it would be mostly non-significant results. Just by chance, though, because we were lucky or unlucky, depends on how you want to see it, we would have had some results that would be significant. How many of those would be out there? Well, proportional to what would be the respective error rate. So it would look pretty much like a normal distribution, not like a bimodal as it is now. Now, if you start believing that there's some foods that have some association, then you would see some heavy tails at the ends of significance on both sides. But again, most of the action would be in the middle. So it seems that there's a huge amount of evidence that is missing. That central piece, the majority of the evidence seems to be missing here. Where is it? What do you think? File drawers. So what would be a file drawer problem?
You're an employee, not a partner. You can say you're not associated to your...
Okay, yeah. So one is that there are such studies. So now we're becoming paranoid, and we say this is 1,000 studies that have been published, but there's another 10,000 or 100,000 that have not been published. And where are they? I don't know, but they're out there. I believe that there are studies out there.
Okay, go ahead. She wants to be associated, okay?
Okay. So another possibility is that there are not really any other studies out there. This is all that there is. But however, the studies that do exist, the authors were creative about their analysis. So they deviated one way or another. How about meta-analysis? The gray color, this is results that are in fine print. So if you read the papers more carefully, there are additional p-values hidden for primary outcomes, but you need to read the appendices and supplements and fine tables. So there's some of that middle ground that is filling up, but not necessarily to the point of solving the problem. Some of that information has been relegated to fine print but there's still far more missing, which could be either studies that don't exist or studies that have had the results distorted creatively, intentionally, unconsciously, consciously, so as to get interesting, significant results. How about the meta-analysis, which is the other panel? What do you think about that distribution? These are meta-analysis of these same associations. So meta-analysis possibly have solved some of these excess significance problems because some of the extreme positive and negative studies have canceled out in a way. But it's still not what we would want to see. It's very difficult just to take fragments of published evidence, especially if they have been distorted with some selective reporting, and just expect the meta-analysis to solve the problem and get reliable evidence out of the pooling of these results. Are there any interventions that have very large effects? By large effects, I mean things that clearly work, that, for example, improve outcomes fivefold. So if 10% were to get better with standard of care, we have some intervention that increases that 10% to 50%. If you think about your specialty, things that you do, are there such things out there? Antibiotics? Give me some more specific examples. I'm really asking. I told you, I have no clue. But
Yes. So once again, back to you, Lindsay. Enough about me. So you are
But in your field?
impress all of them by telling you what you think is happening when you're talking isn't really happening.
Okay. When someone does have an infection, give antibiotics versus not giving antibiotics. For any type of infection?
Happen, what you want to have happen, happen. So I'm going to give you the specific pulse. How to get done what you want to get done. Keep doing, Lindsay, you're on fire.
Done.
Yeah.
How does that spoil conversation?
Right, then at the end, once you're frothy, thinking that everything is just
And what would be the baseline?
about using words and coupling of words that are hurting your
So would that translate to a fivefold improvement compared to?
authorities. See, so you're going to agree with me that they're not good.
So not really fivefold, but clearly effective. So there's lots of things that are effective. I have no doubt about that. But really huge effects in clinical disciplines are not that common. And this is a paper that I published a few months ago, where we looked at 85,000 meta-analysis, the entire Cochrane database of systematic reviews. How many of you are familiar with the Cochrane database? So, okay. About 220,000 randomized trials. So the more robust, rigorous type of design, you have randomization in place, so hopefully lots of the problems of observational studies would go away. And the question that we asked is, how often do we see trials that have odds ratios more than 5 and also nominally significant results? It was not uncommon. It was almost 1 out of 10. So 1 out of 10 times, you have at least one trial on a specific question that gives such a big effect. However, almost always, these trials had exaggerated effects. So when we did another trial, that effect went away. It was completely dissipated or became much, much smaller. So, and these trials that had these odds ratios of 5 or larger, their average sample size was 14 people. So we're talking about very small studies that really didn't have such strong evidence. How about things like mortality? If you take these 85,000 meta-analyses, which are pretty much the whole of medicine, well, not the whole of medicine. It's about 50% of medicine, because the Cochrane database is a work in progress, and it has covered probably about 50% of medical interventions so far. So how many medical interventions decrease mortality 5-fold The evidence is nominally significant at a p-value of 0.001, so more stringent than just 0.05. And there's no clear evidence, obvious evidence of bias. How many would you think out of the 85,000? Give me a number. 0. Oh my. Okay. 5. Any other thoughts? This is the entire clinical medicine with all its branches and disciplines and specialties. Couple of thousand. Well, 85,000. But not all of these were mortality. So I think there are a few thousand mortality forest plots or topics here. Maybe 100. Okay. So we found one. Extracorporeal oxygenation for premature babies. And the question is that all? So how about insulin? You have someone with fluoride diabetes, he's going towards coma or ketoacidosis, and would you ever randomize that person to get or not get insulin? Insulin was developed at a time that we didn't have randomized trials. So we never had the ability of proving that it works so much. Or penicillin. There was never a randomized trial for penicillin, because again, it was developed in 1940. At that time, there was no randomized trials. We started having randomized trials in 1947 or so. So there's a few more, and Paul Glasziou has a paper in BMJ with about, I think, 20 interventions that have big effects, or supposedly. We never tested, and we can't really go back and test now. But
that gift, and this is the sexist slide.
Yeah, what do you think? Flu vaccine. First of all, let's define the outcome. So, mortality? No. Not for mortality.
Old people that get the flu die. Old people die without
A little bit, really loud.
to repeat over and over.
She thinks that when she's talking.
So I'm happy to discuss whichever outcome you want, because obviously the effect size will depend on the outcome. So we can talk about mortality, we can talk about hospitalization, we can talk about symptoms, we can talk about symptom resolution, we can talk about complications like bacterial pneumonia superimposed. But if we start from mortality, is the flu vaccine so effective as to cut mortality 5-fold? Not really. Okay, I think that it does cut mortality. Actually, we have no good evidence that it cuts mortality. I mean, we have some evidence on other endpoints that seem to be improved. But I'm willing that maybe there is some mortality effect, but if it is there, it's going to be like a 5% relative risk reduction or 10% relative risk reduction, which is, we shouldn't say that this is nothing. Sometimes a relative risk reduction of 1%, if you take it to a population level, it could make a difference. So coming back to the nutrition example, if one more serving of fruit and vegetables is decreasing cancer risk by 1%, if you take that to the global population, we're talking about tens of thousands of cancer cases that could be averted. It's not negligible, but it's a 1%. It's not. It's a relative risk of 0.99. Same thing for flu vaccine. If we have a 5% relative risk reduction in mortality, it could still translate to many deaths averted. Although the evidence for death actually is not so strong. It's mostly for other types of outcomes that we have some more solid evidence. So big effects are not common. Most effects are pretty small. And this is just a plot showing at what happens to the effect sizes when we have a first study that shows a very big effect, and we have subsequent studies on the same question. The effect sizes tend to become much, much smaller. So here's some simple definitions. Credibility is how likely a research finding is to be true. Significance is how likely a research finding is to attract attention. And statistical significance is a key criterion for attracting attention. Now, this is not a joke. This is why statistical significance was developed early on in the 40s as a way to attract attention. You know, people really wanted to flag some findings that deserved more attention than another bulk of evidence. In a way, when people were doing this, they were trying to replace some other type of thinking, which was the Bayesian thinking, that was also trying to tag research findings with one or two or more asterisks based on the attention that they deserve. But they did it in a different way. They did it in a way that they had some explicit testing and trying to generate a p-value for the specific null hypothesis and the alternative that was being posed. Credible has very little to do with statistically significant. In some cases, they have some correlation. So some credible findings could be statistically significant, but many statistically significant findings, like the ones that I showed you in nutrition, are not credible. And many credible effects or associations just are not statistically significant when we test them. Why would that happen? So it could be bias operating in the opposite direction, that even though there's something there, there's conscious, subconscious, or unconscious bias, that effect goes away. Could be small sample size, that we don't have the power to show that there is a difference, that there is a benefit. It could be the statistical analysis that is not efficient, that we're using a model that doesn't have the best properties to discover that. So credible and statistically significant are sometimes correlated, but not that much. Almost all studies are statistically significant. So this is an empirical evaluation that I did a number of years ago. We looked at 389 epidemiological studies in major journals, not just nutrition, just all over the board. And 89% of them highlighted statistically significant relative risks. Actually, in some journals, the significance rate was 100%. Yeah?
The tears that's happened in front of you. But we're going to work on this very hard today with your permission. Is that okay? Mm-hmm. Just because you're right doesn't mean anything significant has happened. All right. Ready for the depression to be over? And there's the mic there. And could you hand the mic over to whoever you like?
Now with his improvement,
My name is Peter Shaw.
but you take that in the individual, and if only
Stay
maybe
classy,
100
San Diego.
people will get
Yes. You know how long I've waited to say that? Go ahead.
Speed is the biggest enemy
applying it to
creating
individuals.
system.
So it is a problem in a way that for individuals, it's going to be a yes or no. So they will either get cancer or not get cancer. It's not that they will get 1% of cancer. I have a diagnosis of 1% cancer. This is always a problem. But most of the time, we're just stuck to working with population averages. I mean, we can try to individualize and try to identify subsets and subgroups and smaller clusters of individuals, and ideally eventually pinpoint to the specific individual who will get whatever. But once we go down that path, we really need even more evidence, because then each subcluster, each subgroup requires evidence for showing that they have high or low or intermediate risk from scratch, in a sense.
Realize I'm not going to get out of this
Yeah.
quickly, nor should I. So could you please read the next one, because they go together.
Starting now, slow.
What would maybe mean?
Go ahead.
In each communication, in delivering each communication, in engaging after each communication.
Okay.
Okay, well, this is at the level of diagnosis then. Yeah, I guess you can give a probability of having a diagnosis. This is a little bit different, or you can give a probability of getting cancer that hopefully, if the model is well calibrated, when you take a larger population of similar people, the percentage of people who do get cancer is the same as that you have predicted.
Blanket statement that I've got no data to back it up with, but I've worked with a lot of doctors.
That's an issue of defining the outcome. So you can define cancer as any cancer, or as cancer that has a given stage or a given size, or is metastatic, or depending on what the cancer would be. So and the probabilities would be different depending on what the cancer definition is in each case. The good thing about this type of analysis is that the Cochrane collaboration has all of these information in forest plots. So these forest plots are easy to move to whatever statistical software you want. So you can move them to R or Stata or whatever. So you can work directly with the forest plots. And this is a big advantage of this whole movement of evidence-based medicine, that now at last we have evidence that we can work on and see where are we and what are we doing. I also want you to think about what is really a study. So if it's a prospectively designed randomized trial or a prospective cohort where you start collecting data, you have a specific aim and specific outcome that you want to go after, then clearly this is a study. But if you have a data set with 2,000 variables, what defines a study? I mean, you can go to that data set and click a button and test a 2x2 table. And that seems to be an interesting result. And then you say, I'm going to start writing this up. It's a highly exploratory analysis. Does it qualify for a study? It could become a study. It could become a published paper presenting a very nice looking story about that. But it's not the same as a crisp study that has boundaries of start date, end date, predefined outcomes. And much research is of that exploratory type. So what you're describing is allegiance bias or confirmation bias. If you have a strong belief on how things should be, then maybe you interpret results in a way that they should be consistent with that. And if they're not consistent, you suppress them or change them. And this is a major problem in exploratory research. It could be a problem even in prospective research, even in randomized trials. If you have a strong belief on what you should find, sometimes there's leeway analytically that you could distort the evidence, intentionally or unintentionally, that you would get a result that is consistent with that confirmation bias that one may have. Okay, so are non-significant results useless? Not really. I mean, they could be even more useful than significant results. So statistical significance has no correlation practically with the importance or the utility of the results or the information content of a result. Sometimes a completely null, seemingly null result may be extremely informative because it gives a final answer to a hotly debated question, and you know that this is null. You don't need to waste more time on trying to pursue that further. Conversely, sometimes a significant result, nominally significant result, could mean very little. Maybe we know that already. We had 5,000 studies showing that, and this is study 5001. What do we learn out of this? We learn absolutely nothing. So the information content of a study is not related to its nominal significance. But I'll show you a few more examples. This is one field of tumor markers. This is a huge literature. There's about 2,000 papers published every year on markers that are associated with what happens to different tumors. So people with cancer who have that marker die faster or develop metastatic disease earlier and so forth. And these are two data sets of such studies that we looked at. On the left hand, it's 340 studies that had been included in prognostic marker meta-analysis. And on the other side, it's 1,575 studies that had been published in a single year in 2005. And other than that thin slice, which is 9.4% and 4.2%, everything else was nominally statistically significant in that literature. So 91 to 96% of the results had suggested that we had found a nominally significant tumor marker. So 2,000 papers per year, about 50,000 papers for that literature until now, how many tumor markers are we using in clinical practice? How many would you say? There's about 50,000 papers, and 90+% of these papers have significant results. Okay, a little more. It's about a dozen. But, you know, a dozen out of 50,000 papers is a very low yield. And actually, if you look at even those results that are quote-unquote negative, the way that they're presented, they're not really admitted to be fully negative. So many of these papers that have quote-unquote non-statistically significant results, they claim significance for other analyses, which are non-prognostic. They discuss non-significant trends. So they take a p-value of 0.07, and they say that we saw a strong trend, or even not even so. They would say we saw an effect. It could be a p-value of 0.07. It could be a p-value of 0.20. It could be a p-value of 0.40. It doesn't matter, because they feel that, yeah, there is something here. Or they would offer apologies. Now, this is an interesting category. It's all the situations where people are not willing to abandon ship. So the classic example is a paper where there were 127 p-values scattered throughout the abstract text tables, all of them very far from a p-value of 0.05. None of them was nominally statistically significant. However, the conclusion of the abstract was that this is a very important tumor marker, as we have shown in our previous study. So, you know, the evidence had no impact on the conclusions.
Fly back to Tampa from New York and say, honey, look, I understand I'm not supposed to date.
They were unlucky. The expectation would be at least 5 or 6, but you know, it's an expectation that also has some variability. They were very unlucky. Well, because some journals would publish these papers, and I think that more and more editors are sensitized that they shouldn't select papers based on nominal significance. I think that the majority of editors have heard about that, and I think they're trying to do something. I think that they realize that it's important to publish well-done studies rather than just nominally significant studies.
Not just that, it's misleading.
Absolutely. There's actually some work by Dan Fanelli, who has worked on different scientific fields and has mapped the proportion of papers that have nominally significant results. And the proportion tends to be higher in what one would call softer sciences. So physics, for example, whenever it has empirical testing, the proportion of significant results is much lower compared to medicine. Medicine is lower than psychology or behavioral science. The lowest, I think, is physics, and followed by chemistry. The highest, I'm not sure whether I have that slide. I think it's some of the psychological sciences.
Looking at some of the blueprints and give some input on the layout.
Really loud?
Well, ecology is actually not doing that bad. I mean, if you think about global warming, I think the evidence is pretty strong. I mean, for many of the key claims, you know, one could debate about the exact magnitude of the effects, but typically these are very large databases. They have collaborative structures. It's not that they have just one scientist analyzing piece of data. They have ways that there could be cross-checks in what is being done. So I think in terms of reliability, this is a field that's pretty high in terms of reliability. So if you exclude those that claim that there is something significant, 98%, 98.7% claim that they had found something that was significant and even worth it. But at the end of the day, out of these 50,000 papers of tumor markers, we only have 12 markers. So somehow this statistical significance does not translate to something that is useful and possibly not even credible.
Years ago, $22 million in the war chest, and the highest name recognition of anyone in the history of the Iowa caucuses. And she went in there, I didn't come up with this Candy Crowley on CNN, so I'm not going to take credit for it. She went in there thinking the action she wanted was to...
It could be. I think that it's a constellation of many factors. And I will try to dissect some of those. Some of those are misunderstandings, obviously, and others are very clear understandings, but people choosing the wrong things to publish. So practically the reason that research findings may not be credible, there's two clusters of reasons. There's bias and there's random error. And random error, you can also see that from the perspective of multiple comparisons. It means that there's many analyses that could be done, and just by chance, some of them may end up being nominally significant. Out of 100 analyses, 5 of them would be nominally significant just by chance, even though there's nothing there that represents a genuine effect. Now, if you think about how many scientists could be performing analysis, how many scientists are out there? How many scientists are publishing in biomedical journals, in life sciences and biomedicine nowadays? 100,000? Any other estimate? 15,000? Any other estimate? 25? So if you go to Scopus, which is a citation database, it includes life sciences, it's about 15 million. And obviously life sciences are a big chunk of science, but if you take other sciences, then there's about 30 million scientists who are publishing scientific results currently. They're out there. They're out there doing work and publishing. You know, obviously that includes people who have just published a single paper. So it could be some students who are working in a lab and just published a single paper. But they're scientists by all means. They have published in the peer-reviewed literature. So if you have 30 million scientists working with analysis that sometimes are extremely complex, and some tools like genetics, you can measure 10 million gene variants. So you have an extreme multiplicity of analysis that could be undertaken, and just by chance, you may end up having lots of nominally significant results. So random error could be a big issue, but then there's also bias. And there's just lots of possibilities about what bias may ensue. By bias, I mean here any deviation from the truth beyond the chance error component. It could be conscious, subconscious, or unconscious. So it could be that someone has deliberate effort to generate one type of result because they will make money, or because that will save their grants, or will promote their career, or whatever. It could be subconscious, that they want to discover something and they have some confirmation bias, as I mentioned earlier. Or it could be unconscious. Much of the scientific discovery process, you need to think in biased ways. You need to think out of the box. You need to think about some distorted way compared to what is already known. So this is not necessarily bad. I mean, we need that to a good extent to develop new ideas and to be able to test them. So one may create theory or theories about bias, or one may study its consequences. And theories are seemingly more robust, but it is the latter, it's the consequences that we measure, we can witness, and if it's for health, it also involves patients who would suffer from these biases. This is one field that went through a non-replication crisis. Genetics, I believe, has been one of the most successful fields. But it has been successful in recent years where we managed to take that inherent multiplicity into account. So currently people say that I will not trust a genetic association unless I get a p-value of less than 10 to the minus 8. So very stringent criteria. Or equivalently, they might say, I want a base factor of at least 1 million. And we can discuss what a base factor of 1 million would mean. It means that your credibility goes up 1 million-fold based on the data that you have compared to what you thought before running the study that you have. But in the past, we were running genetic associations just in the same way as we were running nutritional epidemiology. And these are all examples of associations of genes with diseases that were proposed by a paper that was published in a major journal like Nature or Lancet or Science. And I'm just showing you the trajectory of the results as we accumulate more studies, we increase the sample size, and we recalculate the summary result expressed as an odds ratio. An odds ratio of 1 means there's no association each time we get a new study. So in all of these cases, the first study came out in a major paper, nominally significant result, but then as we did additional studies, the effects went away. And at the latest update, it was very close to no effect at all, and it didn't even have nominal statistical significance at the 0.05 level, which based on what we know now, based on the complexity and the multiplicity of the comparisons, even a 0.05 would absolutely be meaningless. Here's another field where one would expect more rigorous evidence. This is cardiology. I selected cardiology, and in particular myocardial infarction interventions, because this is the one field in medicine where we have taken the step of performing randomized trials that are very well done. They're collaborative, they have central analysis, very rigorous protocols, and clearly we have made a lot of progress. If you look at mortality rates from myocardial infarction 30 years ago, they were 20%, 25%, and currently they're like 3%. So over time, we did improve outcomes based on rigorous evidence from well-conducted randomized trials. However, there's still, even in that case, several examples where we were misled, even by randomized trials. Now, this is a similar plot to the one that I showed you earlier. The one difference is that as we accumulate new evidence, new studies, I'm not showing you the cumulative treatment effect. I'm showing you the change in the effect as we add one more study. So these are 10 interventions for myocardial infarction. And if you see a flat line at 1, this is ideal. This is like the brain-dead electroencephalogram type of paradigm. It means that the next study didn't change the results at all. The change, the new odds ratio compared to the old one was 1, so no change at all. And the following study, again, had no impact on the evidence. Again, exactly the same summary result and so forth. But if you see fluctuations, it means that the new study changed our perception of whether that treatment worked or not. And if you see big fluctuation, it means that it changed our perception a lot. We do expect, when we have limited evidence, that new studies will change our perception about how much a treatment works, because with limited evidence, we have lots of uncertainty about how much it works or not. So a new study may make that estimate more accurate, and it may change substantially. So we do see some fluctuation early on, but in most cases, we see that once you get out to 4,000 or 5,000 patients, subsequent studies don't really change our estimates of effect substantially. But there's 2 examples, the ones in bold, where there's big changes in the treatment effect. And these are nitrates and magnesium for myocardial infarction. In both cases, we had early studies, randomized trials, that suggested that we have big benefits. So the first studies on magnesium, for example, claim that you just have to give a little bit of magnesium and you will cut mortality by 50%. Very simple, very cheap, no side effects, just give a little bit of magnesium and you will save half of the people who were supposed to die. And then people started using magnesium, but they said, well, this sounds too good to be true. Why don't we run a large randomized trial? And they did that, and they run Limit 2, which was a randomized trial with over 2,000 people. How many medical interventions have we tested with randomized trials of 2,000 people? What would be your guess? Very, very few. I mean, most drugs get licensed with randomized trials of a few hundred people. And if they make it, then they get licensed, and then they're used by millions. But actually, in terms of being tested, they have been tested in trials of a few hundred. So that trial with more than 2,000 people actually showed a statistically significant result, not a 50% relative risk reduction, but a 25% relative risk reduction in mortality. Very nice. I mean, there's not that many things that decrease death by 25% on a relative scale. Everybody should start using magnesium, but still some people felt that, I still don't believe that. Is it easy to randomize people into a new randomized trial? Ones you have shown in several small trials, and also in a trial of 2,400 participants or so, that it does work and it does reduce mortality? No. How many people would do it? Nobody? How many people would not do it? A few? So practically, in that case, that trial did happen. And it was a 58,000 participants trial. It was ISIS-4. And what did it show? No difference. Magnesium actually increased mortality. But not significantly so, but the trend was in the wrong direction. So what do you do now? How many people would run yet another randomized trial? Nobody? How many people would not run another randomized trial? Several. Those who would not and also would, or none of those, what would you do? I mean, what would you do now? Would you use magnesium if that was your choice to? No. You think it's a dead issue? Okay. So people did manage to get funding to run yet another randomized trial with about 11,000 people. 58,000. Why would you do 11,000? Well, because someone mentioned earlier that maybe there's some people who would benefit. And they selected the people where they thought they would see the maximal benefit. So they run that trial, and what is the result? This is the subset that, based on the earlier evidence, had the best chance, and it had the most favorable results. In the early studies, these people really made it through, and nobody died. And even in the ISIS-4, there seemed to be a trend for a benefit. In that subset, it was people who did not get other interventions, did not get thrombolysis, were older, and so forth. What was the result? Better? How many people think it was better? Many. How many people think it was not better? Fewer. Okay, it was not better. So if you plot that, magnesium has this type of a pendulum behavior with very big fluctuations about our perception of an effect. And actually, I forgot to say that after that, there were additional small studies still claiming, yes, there is a benefit. So studies have gone up and down like a pendulum that doesn't gravitate to a solution. How often do we see that? Not that often, hopefully. And I have to acknowledge, how often do we get to perform studies of 58,000 patients? Hardly ever. Yeah?
Okay. It doesn't hurt her at all? Doesn't hurt her work? Maybe she has to work longer?
Not really.
Yeah. So in the case of magnesium, I don't think it was economics, because magnesium really costs nothing. So I guess probably there's a manufacturer of magnesium, and probably if it were to be used on every single patient with myocardial infarction, yeah, it could sell a little bit, but we're talking about pennies here. It was not that there was strong financial conflict of interest.
Do this the way I'm telling you to do it right now, and you're agreeing to do it. I'm going to tell you to go home.
Yeah.
And you're going to say, am I fired? And I'm going to say, I don't know.
In many other cases, I think that's definitely the case. There's strong conflicts of interest sometimes that could drive the results or their presentation. I have several such examples to discuss down the road. One has to watch out on what are the exact dynamics in each case. I mean, for magnesium, I think, again, I think that there was a manufacturer, but it's a salt. I mean, it's like, sodium or chloride, or so how much can you sell that? I mean, it's like water. I mean, you can probably sell a bottle of water for a couple of dollars, but I mean, if you say I'm going to sell that for $1,000, it's not going to be easy to convince people. I see. So conflicts of interest are a big topic. I think that I have some examples to show you down the road. They could arise from anything that you can imagine. Actually, this week, I published a paper with Ginny Lenzer, Jerry Hoffman, and Kurt Furberg in BMJ, looking at impact of conflicts of interest in guidelines. And we make some suggestions on how one could, in this influential document that eventually translate to action and policy and choices, you need to make sure that conflicts are out of the way, because you can interpret the evidence in whichever way you want. You can create the evidence and then interpret the evidence in whichever way seems to be best to your interests if you have conflicts of interest. So I'm just showing you these examples because even with the best possible design, sometimes we may get some extreme fluctuations in the evidence. I'm planning to discuss that, about biases in randomized trials in particular in the second module, but clearly a randomized trial, the fact that it is an experimental design and supposedly is protected by randomization does not mean that it doesn't have biases. So randomization may crack down, it may not function, it may be subverted.
About why you know they can do this. So what does she do that works well, Jim, in your office?
Absolutely. So you can have the randomization code break down, you can have lack of allocation concealment, blinding could affect appraisal of outcomes. There's a zillion ways that a randomized trial may lose its pristine advantage of randomization, just because of other things going wrong. Yep.
With her walker, you're so good with the patients. I want you to be good at this too. So get those boats to rise. This is the protocol to getting someone to say, okay, I'm going to have...
Well, the one that had 11,000 was clearly powered. The one that had 58,000 also. The one that was 2,400 also was powered for mortality.
You can do this, but you have to follow the rules.
Something in the range of, in the last one, I think it was about 15%, and the 58,000, something like 10%, and the 2,400, something like 15% or so. So it was pretty high. I mean, it was at the time that people were still dying. No, it was a common thing to happen, unfortunately, yeah. So besides these uncertainty fluctuations of the pendulum, we also have some more common trends. And a common trend, even with randomized designs, even with experimental approaches, is that effects tend to diminish. This we had observed a long time ago. This is from a paper almost 10 years old now. We took mental health related interventions, so drugs for depression or schizophrenia, anxiety, neurosis, and so forth. It was very common to see early studies claiming that these drugs are wonderful and very effective, and then as we did more studies, the effect sizes became much smaller. This is an evaluation of the creme de la creme of biomedical research, looking at the 49 most highly cited papers in biomedicine examining the impact of different interventions. These are papers that had received over 1,000 citations by other authors, and they were both randomized trials and observational studies. I tried to see how many of those someone had been bold enough to perform a larger, better controlled, less biased study to try to see if these claims were legitimate. And in most of these cases, people had done some additional studies. In observational research, 5 out of 6 of these major claims were refuted within a few years by better conducted studies. And for randomized trials, these are the creme de la creme of randomized trials, the ones that have had the most major impact in the literature and probably also to healthcare. About 25% of them were refuted within a few years by a better, larger study on the same question. So even under the best circumstances, the non-replication rate could be pretty substantial. Actually, for observational epidemiology, there's a paper by Stan Young from the National Institute of Statistical Science that tried to update my analysis from that JAMA paper, he claims that out of 52 major claims made by observational studies, how many have been replicated when we perform randomized trials to see whether we see the same benefits? 52. How many of them survived? 5? 2? 1? Well, Stan says it's 0. And you can read his paper. I mean, some people would interpret the results a little different. But clearly, there is a big problem here for this type of designs. These are some examples of highly cited contradicted findings. Vitamin E and cardiovascular mortality. We had 2 large prospective cohorts done by superb teams at Harvard. We also had a randomized trial of 2,000 people, and they all claim large decrease in mortality, that you take a little bit more of vitamin E and you can cut cardiovascular mortality by 50%. So 1 out of 2 people are saved of those who would die. And then we had several randomized trials, some of them larger than the 2000 one, finding absolutely no benefit. Actually, the latest meta-analysis on vitamin E, which includes, I think, something like 100 trials, shows that vitamin E increases mortality risk. So here's what that meta-analysis finds. It says that the summary relative risk is 1.03, and the p-value is 0.04. I'm making this up, but it's very close to the numbers. I don't recall the exact numbers, but you can trust me. I think this is very fair. Relative risk of 1.03 with a supplement of vitamin E per day for death, and a p-value of 0.04. You have to vote for the following options. Do you believe that there is increased risk with vitamin E for death? No increase risk, no decrease risk, or decrease risk? How many people think that vitamin E kills people? Well, even by a tiny bit. Even by a tiny bit. Let's say that there's a few citizens out there who are dying because of vitamin E. Well, I'm giving you the option of trying to kill these people whichever way you want. I mean, yep. You can wait. I'm not saying that they will die, just take the vitamin E and die on the spot. Obviously, it will be a long-term process, most likely, if that were to happen. So the meta-analysis finds a nominally significant increased risk. It's done by superb colleagues. I trust their methods. It's very well done, very meticulous. It's published in JAMA, impact factor of 30-something, one of the top journals, and it's nominally significant. So how many people would think that there are some people who might die because of vitamin E? Nobody? Some people, yeah. Okay. Oh, sure, yeah, but I'm trying to dissociate everything else. I'm just trying to say that, if they were not taking vitamin E, they would have survived. They would have survived longer. So, yeah, obviously they would die of a zillion different causes. But so how many people do believe that there may be a problem with vitamin E increasing mortality? Quite a number. How many people believe that vitamin E decreases mortality? Didn't you say that it decreases mortality, increases mortality, or no?
Some people it probably increases, and some people it probably decreases.
Okay. I didn't pose that as an option, but again, it could be any dose. The meta-analysis suggests that the detrimental effect is on higher doses, but this is a subset analysis, so you have to take it with a grain of salt. How many people think that vitamin E has absolutely no effect on mortality? So many people think that it has no effect. I would probably side on the no effect vote. So even though you have a meta-analysis that's very well done, it has a nominally statistically significant result, I think that if you think about what is the prior perception about vitamin E being a killer or something that saves lives, most of us probably, if we hadn't heard anything about all these studies, would think that this is not a very likely way to save lives or to kill people. So if you start from that perspective with a low prior, a nominally statistically significant result doesn't really suffice to bring your posterior belief to a position that you would say that now I believe that when I see these early studies, vitamin E saves half of people's lives or increases deaths. Another major contradicted finding was hormone therapy in coronary artery disease. Actually, the term hormone replacement therapy was coined in an era where not having enough hormones was supposed to be a disease. And there were specialties created with sponsoring from the pharmaceutical and hormone industry of specialists whose their job was to promote hormones in the population. And every female has to be on hormones. At some point around 2000, that was the motto, that if you don't take hormones, you're killing yourself. Because large studies, again, done by the best epidemiologists had suggested huge benefits in cardiovascular disease, like 3/4 of the risk going away just by taking a little bit of estrogen or combination. And then we have a very large randomized trial like Women's Health Initiative showing that actually there's no benefit, and if anything, there's harm for cardiovascular disease, and there's harm for many other outcomes like breast cancer and many other cancers. There's a little bit of a benefit for osteoporosis, but if you balance the benefits against the harms are far more compared to the benefits. Another example is nitric oxide that was found initially to markedly improve outcomes in adult respiratory distress syndrome. That was a paper in New England Journal of Medicine, the most prestigious medical journal. It was 9 patients, the sample size. They did very well. So, and ARDS, if you end up in the ICU with ARDS, you tend to do very bad much of the time. They did very well. And then there were several randomized trials with 500 patients and so forth, finding absolutely no benefit. And actually in adults, they saw detrimental effects of giving nitric oxide. In other populations, like children, we think that it works. But at least for the original indication that it was proposed and that was highly cited, it turned out to be not effective. Now, here's some other examples where maybe it's not that these things don't work at all, but clearly the early claims were beyond what we found down the road. So flavonoids were reported to decrease cardiovascular mortality by 80% in a paper in The Lancet. And we don't really have randomized trials on flavonoids, but even epidemiological studies currently suggest that if there is a benefit, it would be much, much lower. Low-fat diet, many studies suggesting that it would dramatically decrease colorectal cancer, heart disease, stroke, breast cancer, anything you can imagine. Big randomized trials found absolutely no benefit. Aspirin claimed to be highly protective against heart disease in both men and women. This hasn't been replicated in very large randomized trials. The benefits seem to be small and differential between men and women. Beta-carotene was a big disaster. There were many studies claiming that it is highly effective in preventing against cancer and heart disease. And there was a Nature paper in 1980 claiming that we could chemoprevent cancer by giving a little bit of carotene, basically carrots. And then we had 4 large randomized trials finding absolutely no benefit from beta-carotene. And fruit intake diminishes breast cancer risk up to 90%. Several case control studies published in the 80s and early 90s suggested that. And currently, based on what we know, it may be diminishing breast cancer by 1%, but not 90%. Now, another superimposed issue is that even when we do these larger, better, more accurate, less biased studies, and we refute an initial observation, there could be still resistance to refutation. So this is an analysis that we did, which is a qualitative analysis, trying to see what happens to papers that get refuted. So we took beta-carotene, for example, that Nature paper had claimed that beta-carotene will save the world from cancer, and then we had several randomized trials finding absolutely no benefit. We took hormone therapy. One of the major claims was that hormones, if you give estrogen, you will get rid of dementia. You will decrease dementia by 80%. And then randomized trials actually showed that if you give estrogen, you will increase the risk of dementia in women. And vitamin E, the example that I mentioned earlier. So we tried to see if a major claim gets refuted, do people continue to cite the original study that made the claim to start with? And if they do that, how do they cite these original claims? Do they cite them and they say that, well, we thought that that was so, but it's not really so, because things have changed, our evidence base is completely different now. So this is what it looks like. This is a comparison of the citations that these refuted papers have been receiving against a control group of papers published in the same journal in the same year. So beta-carotene, it's papers published in Nature in 1981, and I'm not sure how easy you can see the plot, but the refuted paper actually has continued to be more heavily cited compared to the average paper published in Nature in the same year. And refutation, if anything, tended to increase the number of citations that it received. And we see that across the board, also for other refuted papers. Why is that? I mean, is it that people cite it because they say, oh, we were fooled about beta-carotene? So we looked at how citations appear, and the rationale behind the citations is twofold. In many cases, like beta-carotene, the citing papers completely ignore the fact that there have been 5 large randomized trials that have refuted the original claim. They say beta-carotene is a very effective chemopreventive agent for cancer. These are papers in the peer-reviewed literature in very good journals, and because it's well known that it's a wonderful chemopreventive agent, here we present the results of our research where we're using beta-carotene or some modified version or some extract to treat tumors in the tails of rats or whatever. And it's a whole line of research that continues testing tumors in the tails of rats or cell cultures or cell biology or immunology or whatever based on the premise that beta-carotene is very effective and we need to know more about it. Why is that? It's hard to explain, but my explanation is that once you are stuck into a research career with a given topic, it's very difficult to abandon ship. I mean, these people probably had invested 10, 15, 20 years of their lives studying antioxidant stress and beta-carotene for tumor regenesis and regulation, and now they cannot just say, I have to quit or change jobs. So maybe you can tell me some stories from your field in that regard. But once you have a field or a belief or a theory that is out there, it's very difficult to get rid of it, even if you have very solid evidence that this is not the case. Yeah.
Action tip number 10, admit when you are wrong, apologize with power and intensity, then move on.
All right. This is the accountability slide.
Well, but one could argue that if they could really change their line of research, if they had more flexibility, maybe they could try to work on something else that had a better chance of being successful. But somehow it seems that there's some isolationism, and some fields don't really accept evidence if it's contradicting what their basic premise has been all along. In the case of estrogen, the things are a little bit more interesting. It's not that they ignore the large randomized trials that have been done that show that estrogen doesn't really work, or actually it increases problems rather than resolving problems. The way that papers cite the original claim that estrogen is highly effective for dementia or whatever, is that they find counter-arguments to attack the large randomized trials and say that they were wrong. So they say that these studies were biased. They had selection biases. They had problems in the baseline risk of the participants despite randomization. There were participant characteristics that led to this type of results. So it was the wrong age. It was the wrong background. They had some concomitant diseases that invalidated the result. There was prior treatment that was given. The symptoms were not the right constellation of symptoms that one should have taken into account. The stage of the disease was the wrong one. The intervention was not given at the right dose. It was not the right mode of delivery or source. The preparation was wrong. There were other interventions given to these women that made a difference. The type of endpoints was wrong. You should have selected different endpoints and outcomes to study that question. Now, is it possible that there's some justification to these arguments? I can definitely believe that there's plenty of room to debate about each one of these aspects of the design of these validation studies. But at the same time, these are questions that were addressed by studies that were very well designed. They were in public view. Everybody could comment that this would be the best possible design to address that question. And everybody agreed when they were launched that that was really the best possible that could be done to address that question. So in a sense, if you come after the fact and you say, well, that's not the way that it should have been done, this is a little bit scary, because then you have spent $1 billion running Women's Health Initiative, and after you have spent that, and after you've had 150,000 participants follow for 15 years, and after you've had hundreds and thousands of investigators working on it, you say, no, that's not what you should have done. You got the wrong answer because you did the wrong thing. So I think that most funding agencies would not give more money to this type of research. At least they wouldn't run yet another randomized trial. I mean, we had 5 very large randomized trials. But there's very little rationality in funding decisions, and there's a very large number of funding agencies that could fund very different types of research. And if we're talking about peer review of papers, peer review of grant proposals is one level of absurdity beyond peer review of papers. There's some types of knowledge that even though you cannot directly modify the genetic substrate, you can still learn a lot from that. So you can learn about how does a disease work, and therefore find some ways to find treatments based on that knowledge. So, or you could use that information for predictive purposes to identify who are the people at higher risk or lower risk who may need to have a different type of intervention. Some may be more aggressively treated or less aggressively treated or not treated at all. Some may even need preventive intervention. So the utility of research at the early discovery, or what we call T0 stage, is very difficult to define. And I have repeatedly argued about trying to rationalize this. I think it's unfair to tell investigators that you need to tell me exactly what you're going to do based on that research activity if you're in the discovery mode. Because who knows, maybe something gets discovered that could find some application in a completely different field. In my experience, I'm using sometimes methods and techniques that were developed in ecology, or in sociology, or in engineering. And sometimes I have been stuck and I don't know what to do, and somebody is telling me, well, we've solved that problem in engineering. And when these people were solving that problem in engineering, they were not doing it for me in bioscience, but now it's very useful for me. These collateral benefits that are difficult to think of at the early stage of hazy discovery, but once you have reached the point that you have data and you have some claims and you have some statements that this is a treatment that will work for that indication, and you go down that path and you reach the end of of the translational evaluation, you get completely negative results, then it's worrisome that you cannot really get rid of that intervention, and there's still people who would continue supporting it. Now, different fields have different standards about how they perform replication and whether they want to see scientific claims replicated. And some fields change over time, even dramatically so. So this is a paper that was published in Nature in 1994. It's early genetic epidemiology, and that paper studied a couple of dozen people with cerebral malaria. It found that a gene variant in TNF-alpha is associated with cerebral malaria, and it was heavily cited. It got more than 1,000 citations within the first decade or so. And this is the breakdown of the type of papers that are citing that Nature paper. So with blue color, it's reviews, editorials, letters, and news. Papers that have no data, or at least no new data. They're more opinion, and about half of the papers citing the Nature paper are of this type of opinion pieces. This is not uncommon. This is actually the rule across science, that about half of the citations of scientific research are opinions, which may or may not be supported by rigorous documentation. Then you have the black color, which is about 20% studies that cite the Nature paper, but they present data on different diseases and different genes. So they have studied a completely different disease, not cerebral malaria. Maybe they studied stroke, and they studied a different gene. Maybe they studied interleukin-1, and they use in their discussion the Nature paper as buttressing support for what they have found. So they say, we found a cytokine gene related to stroke. And this is probably likely to be true because another paper in Nature found that another cytokine gene is related to cerebral malaria, which is another brain disease. The connection is a little bit remote, but it could help to try to make a case. And then you have papers that are working on the same disease only, and lots of papers that work on the same gene only, but a different disease. You have a slice of papers that are methods, and you also have replications. The replications are with red. And it's not an error. There's not a single paper that is a replication. And actually, that Nature paper got cited over 1,000 times without a single replication ever being done. After being cited more than 1,000 times, there were two teams who tried to replicate this with a sample size 10 times larger, and that was 12 years down the road from the original description, and none of them found any association of that TNF-alpha variant with cerebral malaria. So this is a paradigm that's not uncommon. I mean, there's many fields that are very, very skeptical about doing replication studies. They may see them as me too, or a waste of effort. I don't want to be second. I'm always going to be the first to publish anything. And this is a serious issue because many of these findings may just not be genuine. Now, that same field got completely transformed over a decade. And the reason for that is that we reached a point that there was so much non-reproducibility, so many results that just didn't go anywhere, that people said that we cannot tolerate that any longer. Our replication rate is something like 1% when we try to replicate something. So journals, the very best journals like Nature and Nature Genetics, said we're not going to publish a paper unless you also have very strong replication evidence for what you're proposing. So this is the other extreme, which is what I call ultra-fast replication as a sine qua non. You need to have the replication of the claim in different data sets by different investigators in the same paper. Otherwise, this is not going to get published. And this is a genome-wide association study on breast cancer genetics. These are forest plots from meta-analysis of about 30 different teams that joined forces and by joining these huge data set, they identified some variants that had strong support, and then they took them to even additional independent cohorts by different investigators, and several of them survived that extra replication. And then you know that you have very strong support by 40 different teams. You see that repeatedly. The p-values are something like 10 to the minus 20, and there's consistency in the results across the different teams. And the base factors are something like more than 10 million fold. You have increased the odds of some association being there more than 10 or 100 million fold. So this is one way that one could build these different aspects of the evidence into a grading scheme. And these are some criteria that I created with some colleagues for genetic epidemiology, but I think that they can be applied to many different disciplines. And our effort here was try to revise or update some of the traditional criteria of Bradford Hill. What we're saying is that you need to look at three things. You need to look at the amount of evidence, you need to look at the replication of the evidence, and you need to look at protection from bias. And if you do well on all three fronts, then you get a AAA, and that's strong evidence. If you have moderate evidence on any of these three fronts, then you have moderate evidence, and if you have a C on any of these fronts, then this is very weak evidence. Maybe it's a very stringent type of categorization because you really ask for a lot, but you actually need that. You need a lot of evidence. You need evidence that has been replicated, ideally by independent investigators in different studies and different data sets. And you also need protection from bias, because if all the studies are done with the same bias, you will just get the same results being replicated, but it's just a bias being propagated again and again. Now, here's something that is a little bit more tricky, and maybe we could have a break after that. This is one other way to look at why the amount of evidence is essential. What I have plotted for you is the minus log 10 p-value on the horizontal axis and the log 10 of the base factor on the vertical axis. So p-value based on frequentist approach and testing of null hypotheses, and base factor is how many times our prior odds changes when we get these data that we have in front of us. You see that there is a relationship that is different depending on the sample size where we get the evidence from. So there's lines here for 50 cases, 250 cases, 1,250 cases, and 6,250 cases. I'm thinking of a case control type of study. In that case, this is genetics, but you can think of any type of case control design. And there's two panels, because in the left panel, the minor allele frequency is 40%, on the right panel is 5%. You can think of this frequency as the frequency of the risk factor of interest. So on the left hand, you have a common risk factor that many people have that. On the right panel, you have an uncommon risk factor. Few people have that problem. And you see that when you have a common risk factor with the same p-value and the same sample size, you can get a better base factor. Because you're studying a more common thing, you have more evidence on studying that common risk factor versus studying something that's very uncommon. So if something is very uncommon, even if you have hundreds and thousands of participants, you're studying something uncommon. So what really counts is how many people have the rarest of constellations, outcome and risk factor. Now, if you have a larger sample size, it means that your base factor also is better. And this may sound counterintuitive, because you would say, well, I got the same p-value. Why would the base factor be different? So if you get a p-value of 10 to the minus 6, which sounds very good. And you do that based on a case control study of 50 cases and 50 controls. So 50 people who had bad outcome and 50 people who had good outcome. You run an analysis for whatever risk factor you're thinking might be important, and you get a p-value of 10 to the minus 6. What kind of a relative risk, what kind of an odds ratio would you get to be able to get a p-value of 10 to the minus 6 with just 50 cases and 50 controls? Would it be a small one or would it be a huge one? It would be a huge one. So there's no way that you will get a p-value of 10 to the minus 6 unless the odds ratio is tremendous. So probably the only way to get that is that everybody who has a risk factor has a bad outcome and everybody who doesn't have the risk factor has a good outcome. I mean, even then, you may not be able to get a 10 to the minus 6 for a p-value. So coming back to what we were saying earlier about, do you believe such extreme odds ratios? Probably not. I mean, we don't see such odds ratios floating around. So if we do see an odds ratio of 500, because that's the kind of odds ratio that we will be seeing here, maybe even infinite, we would have a very hard time to believe that that odds ratio does exist. So our prior, even allowing for some flexibility on what exactly that prior would be, would not really allow for a high chance that such an odds ratio would be documentable, I mean, viable to be seen. So even though we would get a very nice p-value, our base factor would not be good enough to take us to a step that we would say, well, now we trust that there is an association, and that risk factor is genuine. Conversely, if we see a small effect, this may be far more commensurate to what we believed ahead of time about how big are effects out there. And therefore, we may be more willing to accept that, yes, now we have documented something that builds upon our prior expectation and is likely to increase the credibility of what that risk factor might mean. I just want to show you some examples here of that exercise being applied to real studies. These are the same epidemiological studies that I showed you earlier on, that almost all of them were significant. I have taken those that are nominally significant, and I have plotted the p-value on the horizontal axis and the base factor based on some plausible assumptions on the vertical axis. If you see a base factor of 1, it means that the results of that study, even though they were nominally significant, didn't really change our prior. And if you see a base factor above 1, in the notation that I have here, it means that the results of that study actually decreased our belief that there is something happening here, that there is some genuine non-null effect. As you can see, that there are several examples where the p-value is nominally statistically significant. All of these cases have nominally statistically significant p-values by selection, but the base factor is above 1, which means that we got a nominally statistically significant result. However, getting that result now, we believe less that there is some association compared to what we thought before running the study. It may sound a little counterintuitive, but it's not if you think more carefully about it. And there's some cases that obviously the base factor is less than 1, which means that the belief increases. But most of the time, we're talking about base factors that are in the range of 0.1 to 1. And in Bayesian terms, these are not results that are more than worth noting. So it's results that one should note down, but nothing more to do with that. It's very, very weak support. It's really the exception that statistically significant results in that literature confer strong base factors that clearly increase 100-fold or 1,000-fold or more the credibility that there is some effect here, that that risk factor is there and there is some non-null effect. So I think this is interesting to take into account, that most statistically significant results do not translate to strong support for the alternative hypothesis that we might be interested in. Okay, I guess maybe I'll start and go through a couple of more minute points as people are coming in. So if they missed that, that's okay. One issue I wanted to discuss briefly was biological plausibility. So how do we pick research questions to test them or to evaluate them? Much of the time we think that some things are making sense biologically, and this is why we want to study them. But in different fields, the strength of biological plausibility could vary a lot. So here's one example from genetics again, where for a very long time we know that there's a gene, apolipoprotein E, that has a specific variant, the epsilon polymorphism, that is strongly associated with the risk of Alzheimer's disease. There's no doubt about that. There's several very large studies, more than 100 studies showing it again and again and again. If you have the bad gene, it increases the risk of Alzheimer's disease 4 times on average. P-value 10 to the minus 350 or something, and base factor of several billion-fold increase. And this is just looking at a single year, studies that have invoked biological plausibility to test the association of that very same gene with other diseases, not the classic Alzheimer's disease, but more than that. So you see that there's papers in the scientific literature that claim that that gene, there's good biological plausibility that could be related to colorectal cancer, to fatty liver, atherosclerosis, hyperlipidemia, acute ischemic stroke, spina bifida, coronary artery disease, glaucoma, pancreatitis, cirrhosis, multiple sclerosis, nephrotic syndrome, alcohol withdrawal, diabetes, migraine. I mean, there's dozens of diseases that people think that there's good biological plausibility that that gene may be related to any of these diseases. And the rationale usually is very convoluted. I mean, they say this gene is associated with Alzheimer's disease, and Alzheimer's disease has some link to migraine. I don't know. And therefore, maybe it's associated with migraine, or it has some link to atherosclerosis. So let's take a look whether it's associated with atherosclerosis. But these are very weak links. So most of the biological plausibility links in the literature are something that you have to think very carefully about whether they're justified or not. I'm not saying not to use biological plausibility, but you need to be very careful. And then this is another example from microarray studies on how external evidence is invoked to support specific types of results, to make them seem that they're legitimate and plausible. For those who are not familiar with microarrays, what we do in microarray experiments, we study lots of genes. Usually we study the whole genome in expression tags, and eventually we find something like 50 or 100 gene tags that are related to some particular outcome. In that case, it could be whether people with cancer die earlier or later, or whether they have metastatic disease. And these are very complex signatures. As I mentioned, they have 50 or 100 genes that are implicated in that molecular signature that could predict outcome. So we looked at 46 studies that were addressing major cancer outcomes in humans, and we scrutinized the comments that were made in the discussion regarding external evidence from other studies that supported or was against the findings of specific genes or groups thereof in the identified molecular signatures. The supportive comments outnumbered the comments against the research findings by 9 to 1. So almost all of the comments that were made in the discussion were supportive of what had been found. But if you look more carefully, 70% of the comments did not even pertain to the same gene as one of those that were found in the study, and 53% did not pertain even to the same disease. Now, you can think that this is a situation where we have an embarrassment of riches. We have 100 genes that we have discovered related to a single disease. There's tons of papers that have studied these genes for that particular disease. And the investigators, instead of discussing any of these hundreds and thousands of papers, they decide to discuss a completely different disease and a completely different gene, which is not among the 100 that we have identified. So people are struggling to find supportive evidence
from very remote connections, even though there would be tons of papers, thousands of papers sometimes, that would be more relevant to the discussion of the specific findings. I'm going to show you some modeling that goes back to the 2005 PLOS Medicine paper and trying to model the overall credibility of a research finding that you will see in the literature. The overall credibility depends on these factors. It would depend on what is the pre-evidence odds, what is the prior, that there is some effect out there that is not null. And as I mentioned, to some extent, this is a function of the multiplicity of comparisons against the true associations or the true effects that are to be discovered. So if you're in genetics, you know that you can test 10 million variants of genes, and you have a sense that roughly about 100 of them would be associated with some disease. So 100 over 10 million, it's about 1 in 100,000. This is your prior for any single one of these variants to be associated with your disease. In other cases, probably your prior is much better. So if you're at the end of the road of clinical development of a new intervention, you have very strong evidence that it works, but you just want to run yet another study, your prior will be pretty high, maybe 50% or even higher than that. It depends on the data, the study at hand. So obviously, if that were not the case, it would be religion, the data would be irrelevant. It depends on bias, how much the inferences from the data are modified or manipulated. It depends on the field, because different fields have different pre-evidence odds. They have different types of data collection and data approaches and different types of biases that are operating in them. And all of these may depend on each other. So here's a simple model where there's no bias and only one team of researchers. This model is not probably very realistic, but the assumptions that it makes is that you're in a perfect world. There's absolutely no bias on planet Earth for anything. You're the only researcher on Earth. You have eliminated all competition. You're the only editor and the only peer reviewer, so everything that you do, which is perfect, will be published in the perfect journal. And this will help you to create your new study, which will also be perfect. So if you think along these lines, you can have this 2x2 table where you have true relationships and research findings that claim to have found relationships. And R is the pre-evidence odds. It's the prior odds of the relationship being true. Alpha and beta are the type 1 and type 2 errors. And C is just a constant depending on how prolific you are and how many experiments and studies you are conducting. So you can see that as a diagnostic test, as the research study being a diagnostic test for discovering the truth, for making the diagnosis that there is some association here, there is some genuine non-null effect. Then you can make things a little bit more complicated, but not that bad. You can assume that there's some bias also. And one way to model bias is to say that some of the results that would have been non-statistically significant, for whatever reason, because there's many different biases, will be presented as statistically significant. So the proportion of statistically significant results in the published literature, in what gets disseminated, will be higher compared to what it should have been. And I showed you several examples that that's likely to be happening quite extensively. So then you have to add a bias term on how commonly would that happen. If you get a negative result, how common would it be that that negative result would be transmuted into a positive result? And you can see what happens with different levels of bias. And then you can also say that I'm not alone. There's many other colleagues doing similar type of research and going after the same research question. And you can think of a scenario where there's absolutely no communication. It's all competition to death or to funding, whatever. It's pretty much the same. And you just want to get significant results. And each one of the teams, each one of your colleagues also wants to get statistically significant results. And if they make it to get significant results, then they publish that. And each one is trying to do that separately rather than joining forces and have a common protocol and a common analysis and a common goal for integrating all the pieces of evidence that are generated. Instead of having that, each one is trying to make discoveries on their own. So then you have to add a term for the multiplicity of the researchers who are looking at the research question, which is that N index in these expressions. And then you can run some calculations that would show you what is the post-study probability of a nominally statistically significant result being true as a function of the pre-study odds, and also as a function of power, and as a function of the extent of bias, the U term, and the number of teams who are trying to discover whatever is to be discovered. And if you do that, you can track it back to some common situations of different types of settings and study designs and research questions that one might be asking. So here's some examples, and I don't have one particular study in mind. I'm just trying to think of broad contexts of study designs and multiple research questions that belong to that context. So let's say that we have a well-powered randomized controlled trial with little bias and with one-to-one pre-study odds. This is usually happening at the end of the translational road. We've done tons of discovery research, preclinical research. We have run some small studies, and now we want to run the definitive trial. Things seem to be okay. There's a good chance that that intervention does work, and we just want to prove it. And in that case, we design a study with 80% power, with 50% chance of being successful when we start. There's empirical evidence that suggests that phase 3 trials have about a 50% success rate, and with little bias, a U term of 0.10. If we get a p-value that is less than 0.05, even a 0.045 or so, then this is 85% likely to be true. It's 85% likely to represent a true non-null effect. That treatment does work. Don't ask me how much it works, but I can tell you that there's a very good chance that it does work at least a little bit. And it could be a lot, but I can tell you that it does work. And if you get a lower p-value, then that 85% may go up to 95% or even 99%. Now, if you have a confirmatory meta-analysis of good quality randomized trials, again, if you get a nominally significant result, about 85% of that would be correct. And if it's even more significant, it would be 95% or so. If you have a meta-analysis of small inconclusive studies and you get a significant result, only about 40% of those would be correct. So even though you get a p-value that's less than 0.05, and seemingly you have accumulated several studies and you've tried to piece them together, in the current environment, about 40% of them would be correct. And 60% actually would be null effects that masquerade as effective treatments or interventions or associations. If you have single trials, if they're underpowered, even if they're well performed, if you get a significant result, less than 1 in 4 is going to be correct. And if they're poorly performed, this will go down to 1 in 6 or 1 in 7 or even less. If you have observational designs, well-powered, and you find a significant result, 1 in 5 will be correct. And I gave you some empirical evidence that's very congruent with that. Actually, if you accept Stan Young's estimate, it's 0%, but I think it's probably a little bit higher. If they're underpowered, it's down to 12%. And if you're in a wild exploratory mode, just going through your database with no idea about what you're doing, just putting variables into 2x2 tables and trying to see what happens, or you say, just throw them all in the model and we'll see what happens. And you have many variables, so you work in a field like genomics, for example. If you get a significant result, it's almost certain that it's going to be wrong. It's going to be like 1 in 1,000, and if you have even more multiplicity, it will be 1 in 1,000,000. And even if you try to do your best to have very accurate measurements and get rid of some of the correctable biases, it will still not be much better. Most of the associations that you will get are likely to be false positives. The worst scenario is when you reach a situation where the effect size is a measure of the bias that is prevailing in a field. You can think of a scientific field that does very poorly, and bias is stronger than the average effects that are circulating in that field, or the extent of multiplicity is such that the few real effects to be discovered are buried under a heap of false positive results. In such a discipline, the effect sizes that you will see would just be very good estimates of the average bias that is operating in the field. So if you study the literature, you will get a very good sense of how biased the field is. That's the only thing that the literature will tell you. It will tell you nothing about what treatment works, what doesn't work, what is the risk factor for this or that. It will just tell you how biased is that entire literature.
You're describing the
I don't know. I didn't want to make that comment because I said I know nothing about endodontics. And if you have different disciplines, and some disciplines find larger effect sizes, and maybe they're scientifically considered to be more successful because of that, then these are simply just more biased compared to others that find smaller effect sizes. Also, within the same scientific discipline, the most seemingly successful and most appreciated studies would be simply the ones that suffer the worst net bias. So this is a nightmare situation. And I'm not going to say that there's one field that does suffer from that null field syndrome, as I would call it. But there are several situations that I have come across literatures that give me that sense of a behavior. Here's one such example. A number of years ago, I was approached by a very brilliant young fellow from China, Zhenglun Pan, and he wanted to work with me on genetic epidemiology. So I asked him how much genetics research is done in China. I knew that China was growing very fast in terms of its research productivity. And he told me there's tons of studies being done in genetics and genetic epidemiology. I was surprised to find out at that time that there's a Chinese equivalent of PubMed that includes more Chinese language biomedical journals than there are English language biomedical journals. There's about 15,000 Chinese language biomedical journals that are indexed, and that I had absolutely no clue about their existence prior to making that contact. So then we said, let's take a look at studies that have or questions that have been extensively studied in the European and American literature with English language papers in peer-reviewed English language journals, international journals. And let's try to see how many Chinese studies are out there in Chinese language. So in all of the questions that we addressed, there were more Chinese language studies than English language studies, number one. Number two, the Chinese literature always found statistically significant results. Number three, the Chinese literature was of better quality than the American and European literature. If you just read the papers, just literally, how did they present their methods? How did they run the experiments? How did they show the 2x2 tables? They were at least as good or possibly even better. So it's not that they were clearly wrong. And here's one example. These are forest plots. If you look at the top left, ACE insertion deletion polymorphism as a risk factor for myocardial infarction. The blue studies are the European and American ones. The pink ones are the Chinese. The Europeans and the Americans found that blue diamond at the end of the day, which is an odds ratio of 1.3, meaning that if you carry that gene variant, the bad gene variant, your risk of having a heart attack goes up by 30% on a relative scale. And the Chinese literature found an odds ratio of 3, which means that the odds of getting a heart attack goes up threefold. It triples. Which one is correct? Well, for that one, we have the benefit of having a much larger study that was done after that with a sample size that is 10 times larger than all these smaller studies combined. And what was the odds ratio for that one, which I think is the best approximation to the truth? 1.1. Any other guess? So English language literature 1.3, Chinese language literature 3, and best approximation to the truth. Actually, I would say this is as close as you can ever get to the truth. One guess is 1.1. Any other guess? 1. 1.00. Absolutely no effect. And you see that same pattern again and again and again. You see a pattern of significant results in Europe and in the US, significant results in China, stronger effects in China. All of these associations that I'm showing you here are based on subsequent evidence and very large studies. We know that the effect sizes are null.
In your prelude to this, you mentioned in your point 2 that the Chinese literature was generally better done. But in point 3, they almost always found 100% of the time a significant effect. Don't those 2 points argue against each other?
They might, but actually one has to ask how much can we understand of the quality of a study based on a published report? You know, a published report is an advertisement that some research has been done. This is the way that I see it.
What do you know about a study other than what they published?
Nothing, unfortunately. Ideally, I would like to be able to see the raw data, the protocol, the analysis code, exactly what was done all the way from conception to delivery to implementation to results. But what you see is really advertisements out there. I mean, the published literature. So someone, and we asked around at that time, why is that? So here's the scenario that I'm building. China is becoming a superpower. Chinese investigators are under tremendous pressure to deliver. You know, they need to publish significant results. Their salary depends on publishing significant results. They get punished if they don't find significant results. And you need to do a good study. So a reported study that looks okay does not exclude the possibility that there could be substantial, extensive, tremendous selection pressure on the results that are to be disseminated. And so there could be tremendous file drawer problem and publication bias, selective reporting of analysis and outcomes. But still, whatever is reported may seem very nice. But it's not validated. And when you try to validate it, exactly because it has been generated under such high pressure to deliver and to perform, it doesn't get replicated. So it's not, you know, the Chinese literature that stands out in that regard. I'm not trying to intimidate the Chinese colleagues. This can happen repeatedly in different scientific environments, in different countries. We had a paper published in PNAS a couple of weeks ago where we show that we see extreme results for behavioral sciences, particularly in the US, because there's very strong pressure in the US in psychological sciences to deliver significant results. Most other countries actually don't do that much of psychological science compared to the US, so we see clear exaggerated effects in psychology in US-based studies. So the post-study odds of a true finding would be small when you have any of these features. And then this is based on the modeling and the equations that I showed you. When the effect sizes are small, when studies are small, when fields are hot, and it means that many furtively competitive teams work on them without sharing and collaborating, but each one of them trying to outpace the others. When there's strong interest in the results, and that could be financial interest, allegiance, or confirmation bias. When databases are large, you have lots of variables that you can play with, and when analyses are more flexible, so you have more options, more methods, more approaches that you could attack the same data set. Now, most of these features actually are becoming increasingly prevalent in most scientific disciplines. So effect sizes are what they are, and as I showed you, most of the time they are pretty small to start with, and there's nothing we can do about it. Studies in many fields are small. Some fields are very hot. Seemingly hot fields, one might argue, well, with hot fields you should get more reliable. Actually, no, because that fragmentation due to the competition leads to single teams publishing extravagant results to try to outpace others. And interest in the results is often financial or other interests. Databases become larger and larger, and analysis we have more flexibility and options in our methods. Another inference from that same model is that a research finding cannot reach credibility over 50% unless U is less than R, which means that bias must be less than the pre-study odds. This is not a very complex inference to make. Just think about it. U is the proportion of null associations that become non-null because there's bias. So if you have 100 associations that you're testing that are null, and 10 of them become positive findings because of whatever bias, then to have 50% chance of finding something that is correct, you need to have at least 10 genuine associations out there among 100. Because even if you discover all of them, you have wonderful power and you do your job correctly and you find all 10 of them, then you have another 10 that were just the result of bias. So you have 10 that were correct and 10 that were just because of bias, so you're at 50%. 10 of the 20 will be correct. If the pre-study odds are low, then you really need extreme protection from bias. If you're working in a field that you can go wild about testing associations and effects, but not too many of them make sense, then you'd better make sure that everything is done in a perfect mode, because you cannot allow missing genuine associations, and you cannot allow building any more bias into this. If you're working in a field where everything is genuine and you have very strong evidence that what you're studying is correct, maybe you can tolerate a lot of bias. So if you're studying smoking, for example, in relationship to cancer risk, we know that this is a prime killer. We know that it kills 5 million people per year. We know that 1 billion people will probably die during the 21st century unless we do something. And probably we're not doing anything. So if you want to study, does smoking cause cancer, you can throw whatever bias you want in there, and still your result will be okay. I mean, you may miss your effect size or misestimate it, but most likely you will still find that smoking does cause cancer. This is another approach on how to deal with uncertainty. This is what I call using credibility ceilings in single studies. And how does this work? You have the option of taking the results of a study based on the point estimate and, let's say, 95% confidence intervals at face value, and say, this is what it is. But then you may want to build some skepticism into that result. So you can say that no matter what I see, because this is just a single study cannot convince me more than 90% that there's something out there. So this means that you keep a 10% that you're not willing to allow your credibility to reach 100% just because it's a single study, and you want to see something more that replicates that. Then in that case, you're using a 10% credibility ceiling that you're withholding until you see some additional results. And you can do that, and you can apply the same rule to each study that is being done. You can say that based on a single study, I'm willing to accept up to 90% certainty. Or you may be even more skeptical. You may say, I'm willing to accept up to 80% certainty. Or if you're extra skeptical, you can say, I'm only going to accept up to 10% certainty, or whatever. And you can introduce that credibility ceiling in the calculations of the uncertainty surrounding the single study results, and also the synthesis of all these results in a systematic review or meta-analysis. So if you do that, this is one example of whether omega-3 fatty acids are associated with mortality. This is a situation where we had, like in many other topics, lots of observational studies suggesting huge benefits, that if you increase your intake of omega-3 through fish or whatever, you can decrease mortality by 50% or 60 or 70%. And then there were larger studies suggesting smaller effects, and actually now randomized trials suggest no benefits at all, or very small benefits. And this is applying credibility ceilings in the original observational studies. And you can see that I have plotted for you a heterogeneity metric, the summary, relative risk in the middle, and the likelihood ratio that there is some effect versus there's no effect with different credibility ceilings. And if you apply more skepticism, the likelihood that there is some effect goes down. It doesn't completely disappear, but it does decrease. And the uncertainty about the effect size goes up substantially. So even though there may be an effect, there's still much residual uncertainty of whether there is one or not. Many fields in very different scientific disciplines have repeatedly found that early discovered true associations are inflated. Now here I'm not talking about false positives. I'm talking about things that do exist, treatments that do work, associations or risk factors that are really influential. Let's say that we are lucky to discover such a treatment that works or such a risk factor that is really important, and we're the first to do that. We are very likely to succumb to what is called the winner's curse. We are lucky because we were the first to discover that association, but at the same time we are unlucky because most likely we got it wrong in terms of how big it is. So it's not that it's not there, there is something there, but on average it's very likely that we have overestimated what association we are after. Now this has been described repeatedly in very different fields, including clinical medicine, clinical trials, early stop trials, mental health, meta-analysis, traditional epidemiology, pharmacoepidemiology, genetics, ecology, prognostic model, psychology. Each field is using a different term. So you will see winner's curse, regression to the mean, fandomship associations in pharmacoepidemiology, the Beavis effect, and there's very little communication between these fields because people don't really work on all of these fields, but they have identified the same phenomenon, that early true discoveries are inflated. And you can think of that of the classic example being whether there is a risk factor for a bad outcome for some endodontic procedure. The first to discover that most likely will find a stronger risk compared to what the reality is. Now, why is that? Well, this is a consequence of the process of making discoveries based on some statistical rules. It's a side effect of statistics, in a sense, a collateral damage of using p-values to identify significant effects or treatments or risk factors. So here's a simulation that I'm doing for you here. Let's say that there are some true risk factors to discover, and the true odds ratios are on the left column, 1.10 or 1.25. Let's say that these are pretty common risk factors, so 30% of people in the control group do have that risk factor. And we're trying to make that discovery with studies that are case-controlled designs and have different sample sizes per group, 1,000, 250, or 50. And we have many such case-control studies being done. So each one of us is running a separate study, and we don't share notes. Each one of us is taking a shot with 50 patients or 250 patients or 1,000 patients. And then when we finish, we say, here's what I found, or here's what I did not find. So if the true odds ratio is 1.10, and we run a case-control study with 1,000 patients and 1,000 controls, the ones who will find a nominally significant result for that risk factor, if we tabulate their odds ratios that they have observed, it will be on average 1.23, which is a substantial inflation compared to the true, which is 1.10. And if we had only 250 patients instead of 1,000, the ones who were lucky to discover that risk factor, they will find a median of 1.51. So even though it's 1.10, which probably is a very weak risk factor, it will show up as a 1.51, which actually would seem as a substantial risk increase. Now, if we're chasing a 1.25 real 1.25, and we're running studies of 50 patients, and we're lucky to discover that risk factor. When we do discover it, it's going to be at 2.73. So it would seem like a very strong effect, a very strong risk factor, even though it is a relatively weak one. It's just a 1.25. The reason for that is that in order to get a nominally statistically significant result and cry, eureka, I found it, here it is, you need to be lucky. If you just get a 1.25, it's not going to be nominally significant. But if due to random error, you happen to get a 5, this will be significant. If you get a 2, it's not going to be significant still. So the only chance that you will be successful is if you're lucky or unlucky to get a very extreme result just by random noise. And then you will claim that this is a very strong risk factor, but actually it's much weaker in reality. Here's another problem that leads to inflation of effects. This is what I call vibration. This is a simulated data set where what I have done for you, I have tried to assess a very straightforward association of one factor against another. And I have done that with different models. I have done that with models where I adjusted for some other factors or did not adjust for those. I have done it with models where there were some gray measurements that I thought I should throw out. They were gray measurements, so I don't know what to do with them, impute them, throw them out. I decided to throw them out. I have done different types of analysis that are more or less legitimate. You know, it's not that they're wrong. I mean, how do you know whether you should adjust for 1, 2, 3, 5, 20, 1,000 factors on a multivariate model? There's ways to do that, and I see that the endodontics literature has several such models, but really much of the time, there's not like one recipe that is the ideal recipe. So you can do it in one way and you can do it in another way. And what I have plotted for you is the results for that effect that we're eventually interested in, along with the 95% confidence intervals. And you see that there's some vibration. It's not the same result that we get. Some of these results are not significant. The confidence intervals cross that vertical line of 1, and others are nominally significant. Some are odds ratios of 1.3 or 1.4. Others are odds ratios of 3. Now, if I report all of those in the published paper, that would be perfectly fine, because everybody could see what are the options that I have tried and what are the results that I got. But if I report only one of these results and I select that result based on some belief that I have that that should be a very strong risk factor, so I pick the best result, then I could be in serious trouble. Then this is how selection bias would intervene, and that odds ratio of 3, even though I report it in the paper, no one else is going to see it again. Everybody else will see the other options in the same study or in other studies. Now, inflation of statistically significant treatment effects can be seen regardless of the type of design. So what would be like the most reliable, largest scale evidence, let's say meta-analysis of randomized trials. So this is the entire Cochrane database looking at statistically significant results from meta-analysis of randomized trials. And I'm showing you the strength of the evidence as a log of odds ratio on the vertical axis as a function of how much evidence we have. And you see this diminishing function. And that diminishing function, probably to a large extent, is a winner's curse phenomenon, that whenever we had the ability to run larger sample sizes, the effect size is dissipated and become smaller and smaller. Now, besides replication, there's another aspect of reproducible research, which I call repeatability. Repeatability is not doing another study, a different study, to try to see whether a claim was correct or not. It is repeating the very same study and trying to see if you can get the same results. Now, to do that, you need to have the raw data sets. You need to have some description of what was done, what was the analysis. You need to have the analysis code. You need to have the protocol. This is doable, and many journals have adopted reproducibility practices. So for example, Nature Genetics, since 2004, they said that we will not publish any microarray study unless the raw data, the analysis codes, and the protocols are available in public view for everybody to use and share. If you don't do that, the paper is not going to be published. So we got in touch. There's actually many journals that have policies to do that. The question is whether they implement the policies. So this is a journal that is the best in genetics, one of the best across all scientific fields, visionary editors that pushed for reproducible practices very early on. The best scientists publishing there. And what I did a couple of years ago, I approached Miles Axon, the editor-in-chief, and I said, can we try to repeat some of the published papers? So he was very open about that, and we got together 4 teams of microarray analysts from around the world, the best in their field, and we tried to see could they repeat the analysis of published papers in that journal. And they could do that for 2 of the 18 papers. In the other cases, they could reproduce some of that, but there were discrepancies. They could reproduce from process data, but not from raw data, and there were discrepancies. Or they could reproduce some of that, and there were also discrepancies. And most of the time, they just couldn't reproduce anything. And the reason for the non-reproducibility and the non-repeatability was that the data were not available. The software was not available. It was kind of a homemade version that had disappeared. The methods were unclear. So we had 4 teams of experts, microarray analysts, but they couldn't understand what exactly was being done. Or the methods were very clear, but the result that they got several teams of repeating microarray analysts, they got a very different result. So this is repeatability under pretty much ideal circumstances. I mean, you have the best journal with the best science from the best teams on what should be at the forefront of reproducibility. So the question eventually is whether we can push for more reproducible research. And to do that, you really need to have more openness and be able to share data more widely. There's one belief that the one who thinks about the research should be the one who also owns the data. But there are some problems with that approach nowadays. First of all, there's lots of fascinating biology and life science research currently that is completely agnostic, which means that we just have a new technology that we can measure lots of things. We have no clue about what these things mean. Nobody can guess which would be the important gene or the important proteomic profile or the important metabolomic or microbiota that is related to the outcome. So it's not that anyone can put any serious thinking into what the result should be. So I would argue in that case, the argument that someone is thinking about what the results might be does not really exist. And the one thing that one could think about is what would be the strongest, more robust study design. And this could be a collective effort. I mean, it doesn't necessarily have to be one person thinking about what would be the optimal design. It's actually much better to have input from methodologists, from clinicians, from biologists, from anyone involved in that technology in order to get the best possible answer. So there's 2 stances in hunting associations and effects and risk factors. There's the aggressive discoverer and the reflective replicator. And they belong to different worlds. The aggressive discoverer believes that what matters is discovery, that databases are private gold mines known to be shared, that a good researcher can think of more exploration. One should report only what is interesting, publish each association as a separate paper, and push your findings forward as soon as you publish them. And the reflective replicator says that we need replication, data are a public commodity, a good scientist is the one who is robust about design and analysis plans. You need to report and publish everything, and just publish one paper, don't salami, publish 100 papers out of a single experiment, and try to be critical and cautious with what you have published and not oversell what you have produced. I think that we need discoverers. I'm not saying that we just need replicators, but we also need to amalgamate these 2 cultures and make them survive and reach a point where our research projects would be more reproducible. I wanted to go through a number of common biases. How many biases are out there? This is a classic paper by Dave Sackett. It was published in the Journal of Chronic Disease in 1979, and currently the journal has become the Journal of Clinical Epidemiology. Dave was trying to come up with like a list of biases that could affect scientific designs like case control studies and other types of clinical research. And he came up with a pretty extensive list. Subsequently, some other investigators thought that maybe there's only 3 types of bias. There's confounding bias, there's selection bias, and misclassification bias. But then there's so many manifestations, and some biases could have components of confounding and selection and misclassification that I've always wanted to come up with an encyclopedia of bias terms. So here is an exercise using PubMed in collaboration with David Chevalerias from the École Polytechnique in Paris. I wanted to create that encyclopedia of bias myself, and obviously to do that you have to read all the biomedical literature, which is, at that time when I tried to do it, it was 17 million papers. Now it's 22 million papers. So you can think of reading a few every night, trying to get there. But David said, why don't we ask the computer to just read the entire literature overnight and see how it looks like. So here's the 40 most common bias-related terms in PubMed between 1958 and 2008. And you see some classic biases like confounding. It is at the top of the list. First appearance in PubMed in 1962, and 21,000 papers that have it somewhere in their title. I mean, obviously there's more that discuss confounding. Selection bias first presented in 1968 in PubMed, but actually had been presented in the psychological sciences much earlier than that. Publication bias in PubMed appears in 1979, but people had described the file drawer bias in psychological science in the 1960s. And response bias in 1961. Again, behavioral sciences had come there first. And more biases that have been described in the literature. So I'm going to skip that. This is just the method that David used to generate a map of bias. It's a paradigmatic proximity map. So what this method does is that it creates communities of terms in the literature that tend to coexist. It's what we call in sociology cliques. And within a clique, you find terms that tend to appear in the same papers. So here's one such clique. And these cliques include, at a minimum, one bias term, but they also include other terms that codify or can tell us something about what aspects of science these biases are relevant to. So where do they pertain? Now, these maps that I'm going to show you have a genericity and specificity index. Now, genericity means that higher genericity pertains to terms or words that are very generic, that could mean almost anything, that are widely used. And high specificity conversely means these are terms that very few specialized people use, and they have a very specific purpose on how they're using them. And they know exactly what they're talking about when they're using them. So you can map different terms in terms of how widely they're used and how generic they are and how specific they are in what they mean. And this is one such clique. You have publication, meta-analysis, publication bias, language bias, and citation bias. So publication bias, language bias, and citation bias are 3 problems, 3 biases that tend to occur in meta-analysis, and they are related to the publication process. So maybe you can tell me what you understand by each one of these 3 terms. Publication bias is the easiest one. So someone, publication bias? We've been discussing about that all morning to a good extent. Well, it could be for whatever reason, but I mean, if you were to give a definition of publication bias.
They only publish articles of a certain type.
Yep. So publication is driven by the results of the studies. It's dependent on what the results of the studies are. If they're significant, then they get published, or they're much more likely to be published compared to they're not significant. How about language bias? I showed you one example of language bias. Right, so that was an example of language bias, that if you read one language literature, the results and the impression that you would get and the effect sizes and everything will be different. And it could go in either direction. So in some other fields, it may be just the opposite of what I showed you. There's some studies, for example, that describe that the German language literature has less significant results compared to the English language literature. And the explanation for this is that German-speaking investigators, when they have a significant result, they try to publish it in an English language journal because that's going to be more visible. But if they have a non-significant result, but still want to publish it, they have German-speaking journals that they would publish the non-significant results. And they would be equally well done and equally well conducted, but they would be relegated to the local journals. Yeah, it could be seen as cultural bias, and it's something that you cannot take it for granted that you know exactly how it would operate. You need to understand the culture of a set of scientists and how they believe that their information should be disseminated. How about citation bias?
Using citations that don't really lend credibility to what they're saying.
So citation bias is a term that connotes that specific results are more likely to be cited and disseminated and be influential compared to other types of results. And typically, it's that significant results are more likely to get more citations, even though they're equally well done studies on the same question. They don't drive that much attention in the literature. And this has been repeatedly seen. Sometimes there could be whole networks of spreading citations of some original, very fascinating result that actually is based on very thin evidence or no evidence at all. And there's clear citation bias in the case of propagating that evidence, that lack of evidence, as something that we do have evidence on. So maybe you can think of examples that you may be familiar from. Okay, so tell me about it.
Well, it's one study that was done on notobiotic rats that's basically the foundation of our entire disease model.
Never been replicated.
Never been replicated, very small sample. And they weren't even trying to prove what we take as evidence for our disease model.
Mm-hmm. So I would be very interested if any of you is willing to take a look at that. I'm not sure, maybe that study has received thousands of citations already. But I would be interested to perform an analysis of how people cite that study. So if it's 5,000 citations, we don't need to look at all 5,000 of them. We can take a random sample and try to see how exactly they cite that study, whether they have any reservations, any caveats are raised, or maybe none are raised, and how is it built into arguments to support other evidence that is being delivered in other studies. Yep.
Do the studies that an author of a paper cite have an effect on whether that study gets published or not? If they cite no studies, does it make any difference?
I see. So whether the number of cited papers affects a publication acceptance rate, I have no clue. Yeah. Well, I think it's mostly because citations are used to make a starting case or build a case, both on why some line of research that is being presented in the paper at hand is important, and or to justify or redeem the results. I would argue that both of these approaches are not necessarily the best ones. I would argue that you would need a systematic evaluation of the evidence and the prior studies before you launch a new study. And at the end of the day, you need to just cite again the totality of the evidence and place your new study against that totality and see how that renews and updates the evidence. But this has not been done, unfortunately, in the large majority of studies that are being published. Ian Chalmers and Mike Clark have written a number of papers arguing that this is not happening and it should happen. And journals have said, especially major journals, that yes, we will make it a prerequisite, but it's not happening. Some funding organizations have started taking a more firm stance on that in asking for systematic reviews to be embedded in applications before a new study is to be launched, so that we know that we have the best view, or at least the best possible view, of the evidence. And then making sure that at the end of the day, you will take that evidence into account in interpreting the results of the study. So this is something that there's some efforts being made, but still. Yep.
You mentioned before that a lot of the citations don't really even have anything to do with the paper under discussion.
Yeah.
So why do they cite them? It just makes them seem better or more important?
Because they use them in a way that they seemingly make a case that they are related. So if you look carefully, they're not. But who is going to really scrutinize every single citation and go back and find the paper and realize that, well, these people are talking about a completely different thing that's completely irrelevant. And sometimes maybe that paper is reaching the exactly opposite conclusion compared to...
Give a paper a weight that it oftentimes doesn't merit.
It gives them a coding of a scientific coding that could probably borrow some prestige of the citations of the citing papers. It's interesting that there are a few examples where some papers have been published in exactly the same form, word by word, in different journals. For example, some of the reporting standards for research. There was so much interest from journals that the journal editors agreed that this is something that should be published in the Lancet and in BMJ and in Annals of Internal Medicine and JAMA and Journal of Clinical Epidemiology, and also lots of specialty journals at the same time with it's exactly the same paper. And obviously people acknowledge that this is the same paper being published in all these journals. It's not that it's fraud. I mean, it's very visible that that's the case. So then the question is, when that paper, which is a single paper, but has been published in 12 different journals with impact factor from 2 to 40, when that paper gets cited, which version gets cited? They're identical versions. Well, usually there's room for one. I mean, you know, I haven't seen people citing 12 times exactly the same paper. I mean, as I said, it's not, they don't vary even in a single word. But which journal's version? So they cite, the number of citations is perfectly correlated with the impact factor of the journals that have published these same versions. So the version that appeared in the Lancet that has an impact factor of 40 compared to the one that appeared in a journal with impact factor of 2 gets 20 times more citations. So it lends credibility in a way, I think in a wrong way, but well, Lancet says so. So therefore it must be true. So I just want to run through a few more cliques of bias terms. This is studies as the generic term. Obviously it means very little. It can be used for any types of studies, and association studies and control studies. And these are two bias terms, stratification bias and population stratification. These are biases that are very common in genetics, where we have lots of case control studies, because population stratification refers to different ancestry of the populations. If the ancestry is different, then you have confounding by the difference in ancestry, and you may get some very weird results. This is screening for cancer. And you have cancer as the generic term, and some other types of cancer, like breast cancer specifically, cancer screening. And these are some biases that could occur with screening: overdiagnosis bias, length bias, and lead time bias. You see that the bigrams appear as well. So you have lead time, but this is lead time bias. It's just that the computer is isolating 2-word items and 3-word items, and This means that they could appear both as the 2-word variant and the 3-word variant. But does anyone want to take a shot? We're screening for cancer, so we're performing a mammography or cervical cancer screening with Pap test, or colorectal screening with colonoscopy, or hearing loss, testing hearing. These are pretty well-established methods, but there are many others that one could test for various molecular markers to try to detect cancer in an early stage. The problems that we run across are overdiagnosis bias, length bias, and lead time bias. What is overdiagnosis bias? It's false positives is diagnoses that you make that are not really necessary. I mean, you know, there are people who don't really have cancer, or they may have cancer that it's so mild and so indolent that there's nothing to do about. I don't know whether that would be a problem in your field. I guess most of the time people come to you rather than you screen for problems that you need to intervene. How about length bias? So how about you screen and you have length bias affecting the cases that you detect? What is length bias? So length bias means that if you apply any screening tool, the cases that you will find, that you will make a disease diagnosis, would be those that are the most indolent, the ones that are developing more slowly, maybe the ones that have the best prognosis. So for cancer, if you have a cancer that is very rapidly growing, kills people within a few weeks, these cases have a very small time window, and unless you hit that patient right during that window, you're not going to pick that person. But if you have a case that would never have caused a problem and that person would never die, or will die of something else, would never develop metastatic disease, it would be indolent, there was something that you didn't really need to know about, and you perform screening in the whole population, you're likely to get lots of such cases because those people, they carry their cancer their whole life, and it doesn't matter. Yeah. So I'm not sure, again, whether there's similar situations in screening for dental disease that, you know, it may be easier to find some of the cases that would do very well, regardless of whether they would have any intervention or not, while the ones that had the more rapid evolution of problems would not be so easy to find. And how about time or lead time bias? This is another problem with discovering cases by screening. So lead time bias means that the screening process will give you a false impression that you're improving outcomes, even though you may not be improving outcomes at all. So I'm venturing into the dental world, but let's say that you perform screening and you find some problems that were not detected earlier. And you do something because you have detected them, and then you see what happens to these patients until they lose their teeth, for example. Very stupid of me to start going into outcomes. So let's say that this is the outcome. and you find that those patients that had been screened and had that intervention done, they did better in the long run. They could really have done better. This is one possibility. But the other possibility is that you just made the diagnosis earlier. They were just anxious that they have a problem for a longer period of time. But the real time of when they lost their teeth eventually didn't change. So they were aware of having a problem for a longer period of time, which is probably not a very good thing. But the intervention didn't necessarily have an impact in improving the outcome in terms of the time that led to the outcome of interest. So in cancer, this is pretty common because we may diagnose lots of cancers that there's nothing to do or there's nothing that needs to be done. And
prostate cancer almost like the poster child for that?
Prostate cancer is a classic example. You know, PSA has tremendous overdiagnosis, clear length bias. You will not pick the really bad cases. I mean, these will come to medical attention much more easily. And lead time, again, is a major issue because you just make a diagnosis earlier on and you think that you protract survival, but you really don't. I mean, it's just that you made the diagnosis earlier, but the patient is going to live the same number of years as...
Living longer with knowledge that they had a problem.
Well, yeah, but not living a longer life. They live a longer proportion of their life thinking that they have a problem, which is not that good. Right. Yeah. Yeah.
Is there a difference between having a cancer prostate test and that one test going by that versus having a progression of every year for 10 years, watching everything, and then all of a sudden the numbers jump?
So there have been different strategies that have been applied with PSA, for example, like how often you should test and whether that would make a difference. But pretty much the evidence that we have is that it's not worth it. So the problems that it causes are far more compared to whatever benefits one might get by picking some cases that might have benefited from somehow earlier treatment. So obviously there has been a lot of resistance. I'm coming back to the resistance to refutation for these change in guidelines for PSA. And can you guess who were the people most strongly resisting the change in guidelines for PSA screening for prostate cancer? So who would be those who would financially benefit? Urologists is one group, yes. I mean, radiologists would be another group.
Drug companies?
Drug companies, yeah, but less so because much of that treatment is either surgical or radiotherapy. There's some chemotherapy as well. But actually, the strongest lobbying in favor of PSA came from manufacturers of pumpers. Diaper manufacturers. And why is that? Incontinence, exactly. So it's a very common consequence of screening, intervening, surgical, whatever, and becoming incontinent. So really that was a big market loss if PSA were to go away. So it's difficult to think who would really be interested in a specific type of research or its implementation. Maybe on that note, if lunch is supposed to be at noontime, we should stop here. Okay, so we're back to biases, and I want to go through a few more communities of biases and cliques of biases, and maybe you could be telling me how they may be relevant to endodontics in various regards. So this is a bias that was first described in coronary heart disease, and this is why you see the generic terms being disease, heart disease, coronary heart disease, and it's regression dilution bias. Anyone familiar with that? But it's not applicable just to coronary heart disease. It's just that most of the literature has been on that field, but almost any field could be affected. So has anyone heard of that? So a regression dilution bias, the classic situation is if you have people who have high blood pressure and they're at high risk of stroke. We know that this is an association that is very well documented. And the higher the blood pressure, the higher the risk of stroke. However, let's say that you have people measuring their blood pressure and they have no clue about how to measure it. So they just take measurements using the blood pressure sphygmomanometer, but they don't know how to use it. The measurements are all over the place. And then we use these measurements to see whether stroke risk is associated with blood pressure. Will we see an association? Will we? Will it be stronger than reality, weaker than reality?
Depends upon the error.
So if the measurements are completely wrong, we may not even see even a mere association to be there, because if people who are supposed to have high blood pressure are measured to have normal blood pressure and vice versa. Some measurements are accurate, others are not. The the strength of the association will be diluted. So the regression of the stroke risk against the blood pressure scale will be diluted. So the more of this type of noise that we have in the measurements, the stronger the dilution of the real effect. So if we have 2 blood pressure measurements compared to 1, for example, and we look at the association of the average of these 2 measurements with stroke risk, the stroke risk will be more strongly associated when we have 2 measurements. And if we have 2 measurements done by more experienced people in more appropriate settings, it would be even stronger. And it would be really stronger. It's not that it would be a fake or spurious result. So the accuracy of measurements, and this could be anything. It could be radiographic measurements. It could be clinical measurements. It could be whatever. If you have noise, the effect size will tend to be diluted. Surveys. Some main problems are participation bias and non-response bias. What do you understand by these terms? Participation bias and non-response bias. Yep.
Non-response bias would be if you send out to get information and you don't get any responses back. So you only take the information from the responses that you get back are the people that show up for the test.
Right. So if you perform some endodontic procedure and you try to find out what happened to your patients 5 or 10 years down the road, and you sent out some, I don't know, emails or make phone calls or whatever information you may have for contact, and you cannot reach them, those who cannot be reached and those who do not respond may be different compared to those who do respond and those who can be reached and do respond. So in what ways? I mean, first of all, the ones who respond are likely to be alive unless you're talking to the netherworld, or while the others, some of them may even be dead. Or maybe they've had a different course of evolution, and it may be unrelated to what happened to the specific question that you're interested in, what happened to their teeth, but it could well be related to what happened to their teeth. You know, maybe one reason that they don't reply is that you know, they had a horrible course and they don't want to hear anything again about what happened to them. So if you have a high non-response rate, you really don't know how that would affect the inferences of the study. And how about participation bias? Non-response is at a follow-up, but how about participation bias? You want to do a study and you try to enroll participants to that, and those who accept to participate may be different from those who do not accept to participate. And you have to decide in what ways are they different. Are they people who have kind of better profile, better prognosis, maybe whatever is happening to them would have a better effect, and this is exactly why they're participating. So the results of a study could be different depending on whether you have everybody involved or just a select sample who says, yes, I'm very willing to participate. And those who participate also may be more adherent to other adjunct measures or interventions or whatever you want to do with them. And they were eager to join the study and more eager to continue working with you, while others probably felt that they didn't want to have anything to do with the study. Yep?
How is this related to inclusion criteria by the person who is doing the study? Is this like in the inclusion criteria, you can have a bias yourself and who you're going to accept and who you're not going to accept?
Mm-hmm.
This is from the other side, the bias?
Exactly. So inclusion criteria could affect participation. I mean, depending on who you try to target, their participation rates may be different. And one has to think ahead of time of what these participation rates are likely to be and how they might affect enrollment in the study and the results of the study if a particular profile of patient gets enrolled or does not get enrolled. So inclusion and exclusion criteria could make a difference in the outcome of the study, even though it seemingly appears to be the same question, more or less.
John, on the non-response bias,
Yeah.
is when you say a high non-response bias, is the calibration of that bias just a linear relationship to the the N number, or I mean, what would you classify as a high non-response number?
It varies from one field to another. So for short-term randomized trials of a few months duration, I would argue that if you see more than 5% people not responding, this is not good news. In many of the short-term trials that we run in my center, we have 98, 99% response rate. However, if you have a survey and you just send questionnaires by mail or by email, often you get 30% or so response rates.
So let's say you have a study of 1,000 people and you don't know what happened to 20% of them. How biased is that? Is there a way to calibrate or state how biased is that study? You had 1,000 patients in the study, and 20% of them you lost. So how is that calculation made?
Well, when were they lost?
They were lost when you actually went to measure the outcome.
Uh-huh. Yeah, so patients could be lost at the last follow-up, or they could be lost in the middle.
Let's say let's say you're only observing one outcome at 5 years. So they're lost. You don't know what happened to them in year 1, 2, 3, and 4. You're just measuring 20% of them were lost in 5 years. How would you calculate the degree of bias in the study with 1,000 patients?
I think that you have to ask whether the missingness is informative. So is it missingness that affects the key outcome of interest? So if it's missingness at the time where you want to measure something that is a primary outcome, that's a big deal. If it's something that is an intermediate follow-up, but you still have the final information, you probably can cover some of that information loss. But many studies, especially those with long follow-up, they may have very large losses to follow-up and very large non-response rates.
Large meaning?
Meaning 30% or higher. Yeah. So you can think, maybe in some of the studies that you're aware, it could be much more than that. How about verification bias and workup bias? These are for making a diagnosis. So you want to make a diagnosis that someone has a particular outcome, that they did well or they did badly, or they had a complication, or they had relapse or something recurred, and you have workup bias. Let's say
we have that. If I did the case, I'd look at it differently.
Okay. So here the tool is that you were involved, but it could be that what you're trying to assess is whether some particular candidate risk factor or diagnostic image or radiographic information is useful to tell you that someone will have a relapse or do badly. And if you have a strong belief that some particular radiographic picture should be associated with a bad outcome, you may follow these patients more aggressively and do more to them or do more diagnostic workup to try to document that they did really do that bad. So unless everybody gets the same handling in terms of how you assess them during follow-up, regardless of what their initial picture was, then you will get workup bias. And an extreme situation is verification bias, where let's say that you want to assess the validity of a non-invasive test for telling you whether someone has liver disease. And the definitive knowledge that one has liver disease would be by biopsy. And you have a molecular marker, and some people have abnormal values for that molecular marker, and all of those do get biopsies to document whether they really have serious disease. But those who have normal marker values, people say, they have normal marker values. Are you going to have an invasive procedure? No. Let's consider that they are okay. Immediately by doing this, we assume that they are okay. But we don't really know that they are okay. We have assumed that they're okay because they had a negative test, but actually this is what we want to find out, whether that test is informative about the fact that they are okay. So we have taken that for granted. In a way, we're inflating the performance of the test by not doing the appropriate diagnostic workup on those people as well.
Isn't that exactly what happens when someone gets a PSA value? They go in to confirm it with an actual biopsy, but they don't biopsy the people that have normal PSA values because that's basically...
So PSA is one such example of a diagnostic test. I mean, those who have normal values would not have a test, and some of them would have had some findings. And there could be also workup bias if people believe strongly in PSA being really a strong marker of cancer. They may just bring people again and again and do more and more biopsies or more imaging until they find something. But this is overworking these cases in terms of the diagnostic procedure and approach compared to others that didn't have a high PSA. So you can think of such problems that would occur in whatever test you perform. It could be a blood test, it could be a clinical test, it could be a radiographic test, and that you're using it to try to make some inferences about what the patient has or may develop in the future.
We have this with cone beam imaging. In other words, the patient comes in for a recall. You take a PA, it looks like it's healed, so you don't take a cone beam. But the cone beam may tell you that your PA is really misleading you, but you never get that information because you look at the PA, looks fine, and you never really know whether it would look fine on the cone beam. So that's a
sounds like
example.
Yeah, exactly.
A better example is actually in our work that uses gold standards. For instance, you're doing a study for cone beam detection of vertical root fractures, and your gold standard for detecting vertical root fractures is a flap reflection procedure, which is an invasive procedure, and you don't subject people where you have a low probability of actually thinking that they have a root fracture to the verification procedure, and it jacks the results.
So these biases are some sort of self-fulfilling prophecy. And I'm not saying that in routine clinical practice one should always go and do that invasive test or a very expensive validation procedure to make sure that they know exactly what's happening, because obviously there may be complications, or it may be just very expensive or uncomfortable to the patient, or have other harms. But if we want to understand the performance of diagnostic procedures and tests in a research setting, ideally we don't want to have that, because if you have verification bias and workup bias, the inferences that would be made would be distorted. So I'm not telling do that for every patient, but within a research setting, the gold standard of tracking what the diagnosis is should be applied equally well to those who have a positive test or a negative test of interest. So here's another type of bias, channeling bias, and we see that in observational studies. And it's a very common type of bias. It means that clinicians prescribe treatment based on the expected prognosis of the patients. So it's not that everybody is treated equally, and it's not that I'm saying that everybody should be treated equally. But if, for example, you decide to treat more aggressively or with your better therapy the people who seem to have the worst prognosis, there's a chance that those people will do worse. And one might say, well, that treatment doesn't work, but actually it does work. But it's just the fact that you started with patients who had the worst propensity anyhow to start with. So they would do extremely poorly. You did your best, and they didn't do that poorly. They're still doing pretty bad compared to others.
So we have that exact thing in when you have a tooth that's broken off, they like to put a post up in the root to try to anchor the crown on. And usually the more severe the break, the more robust the post you use. And so the results of the literature often say that these cast posts don't do as well, but they're generally applied in the more severe cases.
Exactly, exactly. Absolutely. So another way that you will see that in the literature is confounding by indication. So if you have an indication of higher severity, you may go for a more aggressive treatment. and that treatment may seem to be very bad, but it's not bad. It's just that it was applied to the worst cases. This is very common in any field that is operator dependent, including yours. So in the in the entire surgical literature, the best surgeons have the worst outcomes. And you know, I'm sure that you're familiar with that. If it's not the case and you're a specialist, please let me know. But and it's simply the fact that the most difficult cases go to the most experienced and qualified and skillful operators, and eventually you get that seeming discrepancy of outcomes. Now, the only way to get rid of that, for sure, is to perform randomized trial, because then you make sure that whoever gets treated by the best surgeon or the least qualified surgeon, or whoever gets the most aggressive or the least aggressive intervention, this is not dictated by their severity of disease. Can you do it without randomized trials? You may. You may still stick to an observational design and try to adjust for the differences in the severity. There's multiple ways to do this. Most of those do not work very well. Some, like propensity scores and instrumental variables and near-patch matching and some other variants, may do a little better than others, but you're never really sure whether you really managed to adjust appropriately. And there's still not missing information that is very informative for delineating the differences between the two treatment groups. Gender bias, age bias, race bias are pretty common in many different fields. They may be confounded with other types of biases, so populations of different background or ethnicity or age, they may have different propensity scores and different severity of illness or different access to care or different utilization of different procedures and tests, and therefore they may have different outcomes. And sorting these out, how much of that is what you see and how much of that is other factors that are confounded can be pretty tough much of the time. So here's like a map of biases. This is 235 biases in 17 million papers. It's like a galaxy of the bias world. And each one of these circles, if you expand it like the one on citation bias, you see the community that I described earlier with publication, meta-analysis, publication bias, language bias, and citation bias. There's 235 common biases that we identified in that exercise. So that means that even for experienced people, it's often very difficult to think about all the possible biases that could intervene in a research that a design that they're implementing, let alone that they're reading about, where the information may be even more limited. And this is another view of the same galaxy. This is a plot of how commonly these biases are discussed in the literature, focusing on the 40 most common bias terms across 17 million papers. If you see black, it means that nobody is mentioning them in their papers. If you see white, it means that they're very prevalent and highly discussed by lots of papers. Well, here's one more error in the literature. If you read the horizontal axis, I have 1977, 1882. So some things like confounding, selection bias, publication bias, and response bias have become very hot and widely discussed in many papers in the literature. However, if you take confounding, you see that people start discussing it in the 1960s, and by the late 1970s, it's almost white, and then it's bright white all the way. Lots of papers discuss confounding. I would argue that almost every single observational study that you will see in the literature will mention confounding one way or another, somewhere. However, the usual way that confounding is discussed is just a mention in the discussion that observational studies are subject to confounding. Nevertheless, this is not a problem for our study because we tried to take care of this and we adjusted or whatever we did something that solved the problem. Selection bias, pretty much the same thing. Publication bias became increasingly recognized, even though we knew that for about 50 years, almost. It became very prominent in the late 1990s as meta-analysis became very popular, and we had a geometric growth of meta-analysis publications. And there's lots of discussion about publication bias, but the typical mention, again, will be in the discussion that meta-analysis are always subject to potential publication bias. But in our case, our meta-analysis is immune because of whatever reason. Actually, some of that immunity has been conferred by some methodological tests, like, for example, inverted funnel plot tests that are very easy, and they're almost always misapplied because they're applied in the wrong way, in the wrong circumstances, and with the wrong methods. But people run an inverted funnel plot and they say, look at that, there's no publication bias. How do you know? Yeah, it's okay, we're okay. So many of these biases are recognized, but it's not that necessarily the recognition means that they're handled appropriately in the papers. So eventually, this applies to all good research. One needs to protect the study from bias. And to do this, you need to define the question of interest. Try to be very clear about what am I doing here and why is it important. Which is the primary objective and which are the secondary objectives. These needs to be clarified up front. Otherwise, you're entering a highly exploratory spree type of situation that you can get some results that seem very interesting and very difficult to resist once you get them. And then ensure everything that is done with appropriate quality control. So measurements of factors, measurements of outcomes, implementation of treatments, quality controls for procedures, quality checks in the data, logical checks. So if you have a male patient with cervical cancer, there's probably something wrong, either the diagnosis or the gender, or a female patient with prostate cancer. These are not uncommon. I've seen that repeatedly in my own databases, so I'm not really inventing it. I just want to show you a couple more patterns of bias, and then we can probably go through a few papers and a couple of designs that I have been discussing with a few of you over the lunch break. This is the Proteus phenomenon. Proteus was a god in Greek mythology. He was an oracle, and people were trying to get hold of him to ask him important questions about their research, for example. Did I find a true research finding, or their lives, or whatever? He was very difficult to get hold of, and he would rapidly change from fire to water, the two extremes of the physical world. And this is something that we see sometimes in some fields in the life sciences. We see a first study that shows a very strong effect, a very strong result. And then within less than a year, we see another study that shows the exact opposite result. So the first study could be strong effect, the second study would be null effect, or sometimes even opposite direction effect. And then the subsequent studies that are performed fall somewhere in the middle of these two extremes. Most likely, neither the first study nor the subsequent study was correct. But look at the example at the top. This is a genetic association study whether MTHFR variant is associated with neural tube defect. The first study suggests a huge susceptibility effect. The second study finds absolutely no difference. And then the others in the middle have a more modest effect that they describe. And same with the second one. The first study suggests 8-fold increase in risk. Then within a year, we have a study that shows absolutely no difference, and another two that have non-significant results with smaller effects, and then the others are in the middle. The reason that this is happening is that in this field, it's very easy to generate results very quickly. Genotyping can happen literally overnight. These are just 2x2 tables. You can do them on the spot, on the back of an envelope. The paper can be written very quickly, So if you see a paper making an extravagant claim in a major journal, it's pretty easy for a competing team to beat that. So once you have an extravagant result, there is a window of opportunity for a competing team to refute that original observation. That refutation is very attractive while this is still fresh and so seemingly successful. Could this happen in clinical trials, especially long-term clinical trials? So you have studies that take 5 or 10 years to be done. It doesn't really happen. We don't see the Proteus phenomenon in clinical trials. We've looked for that, but it's not there. The reason is simple. If you have a clinical trial that hits a major journal and claims that they have found something very spectacular for a treatment benefit with one intervention, even if someone wants to refute that, they will have to spend 5, 10 years to start the study, collect information, analyze the results, and present the information. So this is not going to happen within 1 year. Then one other aspect that it's important to examine in the literature is whether a paper is listing limitations. The only useful part of the discussion of a paper is really the limitation section. I mean, the rest probably you can improvise on your own on what you think is the meaning of the study and the results. You can interpret them and tell them in your own words. But really what makes a paper be scientific is whether it is discussing its own limitations and telling us what might have gone wrong in that paper. So unfortunately, this is not very common. This is an empirical evaluation looking at 400 articles in 8 top-cited journals. None of them referred in the abstract of the paper to limitations that could materially affect the conclusions. Now, one might say, should the limitations be in the abstracts? I would argue that yes, because for most of us, we have very limited time, and the one thing that we would read about a paper usually is just the abstract before we decide to go to read the full paper. So I think limitations should be part of the abstract, and some journals in the last few years, like Annals of Internal Medicine, are asking for that routinely. Only 5 of the 400 articles had a distinct section on limitations in the paper. So something that you would see separated, that here's the limitations of what has been done. And limitations or similar words like caveats or errors or biases were pretty common in text mining of these papers. But usually they were meant to convey how the presented methods and results overcame, avoided, or circumvented limitations of previous work. So it was not that my paper has limitations, but what I have done has avoided the limitations of previous work, and I have done something that is better. So this leaves kind of an uneasy feeling because every single paper has a lot of limitations. And if they're not stated, the only thing that I can assume is that they're really so major that no one wants to touch them. If you don't see any mention, this is a red flag that that paper could really be problematic. How about editorial policies? If you look at the editorial policies of highly cited journals, they routinely ask for novelty, importance, and significance as criteria for acceptance. Of the 25 most cited journals, only 1 mentions the need to discuss limitations. So it's something that had not been endorsed, but I think that there's a culture change that I've seen the last few years. If you look at some specific journals, Cell is asking for unusual significance. You have to raise provocative questions. PNAS is asking for exceptional importance. The European Molecular Biology Organization journal is asking for manuscripts that deserve urgent publication. And Biochemistry is actually discouraging publication of inconclusive results, which is really a shame, because every scientific result is to some extent inconclusive. It's only dogma and religion that would be conclusive. Then the other thing that you need to examine in any paper that you're reading is whether the inferences are commensurate with the data. And you have to create your own scale in your literature on what you feel is commensurate enough. This could be quantitative to some extent. So if you know what type of question you're talking about, if it's a diagnostic test, for example, you can have some rules a priori that for this type of disease, I'm only interested in diagnostic tests that have a sensitivity of about 90% and a specificity more than 95%, because otherwise it's not going to be clinically useful. You need to decide ahead of time what is the threshold that would make you use that test in your clinical practice? If you have that in place, then you can go back and see, does it fulfill this threshold? And what do people say? What do the authors say for this test that they propose? So this is an empirical study where we looked at molecular diagnostic tests across very different types of diseases. And we found that very few studies had inferences that were commensurate with the data. Most of the time, the performance was mediocre or modest at best, but the inferences were, oh, this is a wonderful test. You should use it in clinic, and it will open new horizons in the management of cancer or infection X or cardiovascular disease. So try to set up your own rules on what is good enough, and then see whether the inferences agree with this. We've talked a lot about publication bias, selective reporting bias, and fabrication bias. Fabrication bias, actually, we haven't talked. This is when you have completely fake positive results. This is complete fraud. So publication bias, is publication bias fraud? No? How many people say no? How many people say yes? Okay, so there's some people who believe that publication bias is fraud. How about selective reporting? So you run 5 analyses, all of them are very well done, and you report just one of them. Is that fraud? Some no, some yes. So this is a very tenuous and nebulous area.
Fraud defined as intent to deceive? Is that your definition?
So I think it goes back to defining exactly what is fraud. So fake data, you create patients who don't exist, analysis that don't exist, collaborators and co-authors who don't exist and have never seen these patients that you're describing. This is clear fraud. I don't think that fraud is common. Some people disagree with that. I think that to become a researcher, you need to go through 120 years of training, harassment, tons of difficulties, no funding, life threats, nightmares, miserable lives. So why would you become a fraud to go through all of that while you can become a politician or an entrepreneur or something else that will get you to make money much more easily? So I think that fraud in science is not common. Actually, I would think that the scientists are among the most honest people in that regard. But this publication bias and selective reporting bias, some people have started arguing that this is fraud and that the scientific misconduct bar should be set at a level where publication bias and selective outcome reporting and analysis reporting are scientific misconduct. Yeah?
If so few studies are actually, they're even attempted to duplicate, how do you really know how much fraud is out there?
We don't know.
You usually only find fraud when somebody
Sure.
tries to duplicate it, they can't duplicate it, and then they confess that they never really did it.
Well, we see the tip of the iceberg. I fully agree with this. I mean, there's far more fraud, but and there's a growth of retracted papers. There's a geometric rise in the number of retracted papers, but we're still talking about numbers in the hundreds of papers out of millions of papers. We have 2 million papers published every year currently, and we have maybe a couple of hundred of them being retracted. So,
but supposing every experiment was duplicated by somebody,
yeah,
most likely the amount of fraud would be more.
It would be more. I fully agree. So this is an inference based more on gut feeling and limited data that I'm making here. It may be that I'm wrong, and it may be that everybody in the room has committed fraud. I don't know, including myself, while I was sleeping. But but I think that this type of frank fabrication, first of all, it's getting more and more difficult to get by with this type of fraud. I think that there's more mechanisms in place that this would be picked up by your colleagues or co-investigators, or it's very difficult to survive. The example by Dietrich Stapel, the dean of the University of Tilburg, one of the most famous psychologists. I mean, he admitted to fraud because he said, I just cannot continue like that. So he had become so successful that he said, I mean, he had started publishing in Science. You know, for psychology, publishing in Science is like unbelievable. And he went to the train station where supposedly his science paper had taken place, where he was supposedly having participants sit next to people of different ethnic background, and he would have litter on the ground in one arm, spread on the ground, and no litter on the other randomized arm. And then he found that when you saw litter on the ground, racism would be evoked as a feeling in the participants. So he went to the train station. He had done none of that, and obviously had found none of that. But he had published a science paper with this, and said, you know, I just cannot go on. I just have to tell people. He also wrote a book. It became a bestseller, made a fortune out of this. So I may be wrong. It may be more common, but there's some debate, and there's a couple of Nature commentaries in the last couple of years that selective reporting bias should become a misconduct, a scientific misconduct item. And there's surveys that suggest that about 25% of scientists admit that they follow questionable research practices, including selective reporting, when they publish their papers. When they're asked about what their colleagues do, the ones that they know about directly, they say that 90% of their colleagues do that.
In our case, Doctor, I mean, I agree with you. It's probably difficult to show intent to deceive, but it would be fraud by incompetence or statistical incompetence, maybe. That they're making mistakes, but they don't really realize that they're making mistakes. Mm-hmm. And it's convenient for them to make those mistakes and not delve further into the details of what they're doing.
Right, right. Incompetence is yeah, I think I am incompetent in much of what I do. I don't have perfect knowledge of the field that I may be involved, or the methods. Much of the time I may be missing pretty crucial information. I think it's the intent to try to do your best. I mean, nobody's perfect. So I think if we start penalizing people for not being perfect, I think probably we're going down the wrong path, because there's no such thing. I mean, it's kind of a asymptotically targeted outcome, perfection. But
everybody would be in jail except Gary.
Yep. So even with the best intentions, I mean, I just want to show you a couple more examples, and then I would like to shift to looking at a few papers and discussing a couple of designs. But here's like the best of all worlds, the best possible world. This is large randomized trials, efficacy trials, phase 3 trials, sponsored by the NIH with no conflicts of interest. The industry is not involved at all. It's about HIV disease, where there had been a very strong, concentrated, and concerted effort to try to develop new treatments. The best scientists were drawn to that effort. It did work. We were successful. We did develop treatments that did change the course of HIV, and AIDS became a manageable disease while it used to be a deadly illness. And this is looking at these trials, how long it took for them to get published from the time that they started. And the two groups are those that found significant results and those that found non-significant results. So even with no conflict and with the best intentions and best scientists and best sponsors and best everything, there's a time delay, a time lag of about 3 years for the trials that found negative results, even though they looked at exactly the same questions as the ones that found positive results. And the difference is not that they were completed faster, they took about the same time, but once they were completed, the ones that had negative results took a few more years to get published. This is another piece that may be also relevant to what you're doing in endodontics, trying to identify risk factors for outcomes. This is one risk factor for outcome. The outcome here is death for people with head and neck cancer. And what we tried to do here is just perform a simple meta-analysis. So we wanted to see whether TP53, which is a marker that has attracted a lot of attention, probably there's more papers on TP53 on cancer than on any other cancer marker, is associated with the outcome of head and neck cancer, in particular survival. So we did a literature search very carefully. We found 18 studies that were published and indexed. But then we said, well, maybe there's more. And therefore, we say, let's look very carefully and let's try to identify every single study that exists on head and neck cancer prognosis and try to see whether there's fine print information. And then we find another 13 studies that had fine print information about TP53 and mortality in these patients, but was not clearly visible unless you took a very careful look. And it was not indexed in PubMed as such. And then there's others that clearly had this type of information, but it was not shown in enough detail in the paper to include it in the calculations. So we get in touch with the investigators of these papers and we get another 10 studies worth of data. And then there's another 23 studies where clearly the data would have been available, but the investigators would not reply. And then there were another 15 studies where TP53 had been measured. It was on head and neck cancer patients. There was no specific mention on death, but the one thing that one would know about a cancer patient is whether he or she died or not. And again, we couldn't get that information. So depending on which piece of evidence you take into account, if you take the first piece, which is what most systematic reviews and meta-analysis would do, TP53 seems to be the strongest risk factor for outcome in patients with cancer of this type. Highly statistically significant, strong effect. If you add the second piece, which is the fine print, but still legitimate studies, then it has a borderline effect. If you add another 10 studies, which is data that we retrieved from the investigators, it has absolutely no effect. And who knows what would have happened if we could have included another 23 studies, another 15 studies, and who knows, maybe another 100 studies that had absolutely no trace in the literature. And this is one more bias that I wanted to discuss, the Lernian-Hydra bias. This is one aspect of multiplicity, and it pertains to outcomes. The Lernian Hydra, for those who may be familiar with Greek mythology, was a monster that had many heads. And Hercules had a very hard time to get rid of it because each time that you would chop off one head, there would be 2 or 3 new ones sprouting from the one that was cut. So for outcomes, it's very common to have a Lernian Hydra situation in that you can think of a very large number of outcomes. So maybe you have standardized things in your specialty, and maybe there's only 1 or 2 outcomes that matter. Maybe. But in most clinical disciplines, if you ask clinicians, what are the outcomes that matter? If you ask a psychiatrist, what is the outcomes that matter in depression? He can list you about 2,150 different scales of response to depression. If you ask a psychiatrist on schizophrenia, there's a paper that lists 666 different scales of response of schizophrenia. And if you look at that example that I have here, this is response of asthma. Patients with asthma, they're being treated with a beta-2 agonist drug. And these are studies that try to see whether a genetic variant affects their response to treatment. So before you can study whether a genetic variant affects the response to treatment, you have to agree on what is the outcome that I want to see, whether it is affected or not. So I would have thought that asthma is asthma, and there should be one way to define response. Actually, there's 425 ways to define response. And these are all the horizontal lines of defining response and analyzing response. There's 425 lines in that slide. Now, if you see black, it means that for that particular study, the citation of the study is on the vertical top, and for that particular outcome, the result was non-significant. If you see red, it means that for that particular study and for that particular outcome, the result was nominally statistically significant. If you see pink, it means that it was nominally statistically significant, but only on a secondary analysis, not the main intention but some exploration or a knowledge exploration, because others could have been exploratory as well, a subset, a subgroup, some adjustment that was not the original intention. And if you see gray, it means that they did perform that analysis. They did report that they did that analysis, but we don't know whether they found a significant or not significant result. So which is the most common color here? White. Yes. White is 95% of the cells here. Now, what is white? White is all the situations where for a given outcome, that particular study doesn't say anything. So one possibility is that that outcome has not been examined at all. The other possibility is that it was examined and it's not reported. And if it's not reported, then you have to wonder, why is that? Maybe it was a significant result and people didn't want to say that they had a significant result. Well, who knows? Most likely, if they don't report it, was not a non-significant result. I argue that most of these studies did look at all of these outcomes, or almost all of these outcomes. And why is that? About 100 of these outcomes are spirometry. What does this mean? It means that someone is blowing into a tube, and then you have a computer printout that gives you 100 numbers. Even if you don't want these numbers, you get them. So you cannot tell the computer, no, I just want to see FEV1. It will give you all the printout with all the numbers, and each one of these numbers could be an outcome. So by default, one has the option to analyze all of these outcomes. There's nothing difficult to do about it. So these are most likely analyses that could be performed, must have been performed, but are not reported. So I don't know whether in endodontics it's so clear-cut on what is the outcome of interest, or whether you have 2 or 5 or 20 or 100 different outcomes. But any sense?
Couple?
A couple. That's very good. You have agreed that a couple are the most essential ones?
Yeah, a few. 3 or 4 at the most. Yeah.
Okay. So even if you consider, for example, clinical outcomes, radiographic outcomes, I don't know, microscopic outcomes, what the patient says, what the endodontist believes. I mean, without being an expert, I can think of
We have, asymptomatic functionality versus asymptomatic functionality, but with radiographic findings, and we have symptomatic functionality, and we have need to extract. Ours is not very complicated.
This is excellent. I mean, I think that if you have managed to keep the outcomes into a regulated space, it's a wonderful situation, because then all the literature could converge to just these very few outcomes. Compared to psychiatry, where things could be all over the place in terms of how to define response. I think I would like to move to discuss a couple of papers at this point. And we can always come back to more types of biases, but I wanted to see some of these papers so that I can learn a little bit about what you're doing. So you will be telling me what's happening here as I go through them. So before we start, if we were to classify that as an excellent study, good study, terrible study, how many? We have three categories. How many people? The best study. How many people agree that this is the best study in the field? Okay. One of the most comprehensive. Okay. So what makes it one of the best studies in the field?
The breadth of data that's used.
And does breadth include sample size or more than that?
There may have been some predetermined criteria. I'm not saying it's a good study. I'm just saying it's one of the best.
No. Well, everything is comparative, so I take it that this is among the best. It seems that there is consensus. At least no one is screaming that, no, it's a horrible study, and the worst that it was done. So sample size, and what else?
Well, it's a big sample size for studies that we see. It's prospective. We have very few prospective studies. It's randomized.
Is it randomized? So I didn't see that it's not randomized, but it is prospective. So the other examples that I came across were mostly retrospective studies. So there's some prospective data collection here, which is good. It's not randomized. What's the main type of information that it's trying to glean? So is it trying to identify treatments that work, or is it trying to identify risk factors that may affect outcomes, or it's risk factors, okay? Is it actionable risk factors? So is it something that if that study is well done, it's risk factors that if I know about their presence and what kind of an effect they have, that would impact on the management of the case. I would do something different, for example. I don't know what that different might be. It would be a different technique, a different follow-up, a different assessment, a different management, more aggressive treatment, less aggressive treatment. Are these risk factors such that would influence your action plan? And would this be based on this study? Does this study offer any evidence that these risk factors, which may or may not be identified, really are such that would affect the action plan? Because I didn't see that, but maybe I missed it.
Well, didn't they do a regression analysis looking at all these different factors that could possibly affect?
Mm-hmm. So it's a study that tries to create a prognostic model practically. It's a multivariate model that they try to generate. And they try to identify among a very large number of factors which ones are the most important for periapical health. In this paper, in part 2, it's tooth loss, if I recall. And they say that we identify 10 factors that could make a difference in the risk of getting that or not getting that. And some of those are protective, some of those increase the risk. But what would you do differently based on knowing that? So you can classify a patient as being at high risk of having a bad outcome or lower or mid-risk.
A couple of those you can. So the absence of a root end filling extrusion would be something where you could change that. You could not extrude out the root end. But most of those, like you said, if there's a perforation or not, that's something that presents in the office and that's beyond your control. So there are maybe one or two that you can change based on this study, but some of the other ones don't seem to be. They seem to be risk factors that just present.
So some of those are modifiable, while others are not easily modifiable. Okay? Yep.
See, I would argue that some of these factors that they identify, aren't necessarily what you were attempting to do. You're not attempting to overfill a root. You're attempting to fill it, properly, but overfills happen so that there are other factors that involve these outcomes that they're measuring that are probably unrelated to the actual outcome, but more related to the presenting factors that we have yet to identify. And you can't identify them preoperatively, and so as a specialty, we just do root canals. If it has this constellation of symptoms, you need a root canal. And we kind of, we have small variations, but you kind of just...
So you would do something, pretty much the same treatment, regardless of what the profile of these risk factors are. So I was, as I told you, I know nothing about endodontics, but it seemed to me that most of these factors are factors that, as you say, are assessed at baseline. Most of those do not seem modifiable. Even those that would be modifiable, there's no promise that if you modify a risk factor and you move it down by 2 points or 5 points or whatever it is, then you bring the patient back to where the original patient who had these 5 points lower risk would be. In terms of what you can do with the procedure. I mean, so the native risk is not the same as the risk that you have generated after an intervention. Okay. So we can talk about things like that may be more pertinent to randomizing. So for most of these factors, I couldn't see a way that I could randomize people to have that or not have that. They either had it or not. Maybe I could do something to try to improve their presentation for some of these factors, but it's not that it's something up to me directly to see them once or to see them twice. to be aggressive or not to be aggressive. Most of those are what they have when they present, and then this determines their risk. So this is a multivariate model, and is that a validated model? What do you think? I understand that most of you have read that paper, but is that, I mean, we said that for prognostic models, for risk factors, you need to have some validation. And you want to see a second population that shows the same results. We also discussed that there is a winner's curse, and that if you're looking for a new association, which could be a new prognostic risk factor, when you first discover it, and especially if you discover it based on statistical significance criteria, and the modeling that they use is standard regression modeling that's using a selection process that uses a threshold of statistical significance, the effect will be inflated. So the average effect that you see for the relative risk will be higher compared to reality. Is that a validated model? It's not a validated. I mean, I didn't see any validation in a different population. To validate this model, one would have to take whatever the final model is that comes after a long stretch of unadjusted analysis to select some variables to be considered in multivariate models, and then putting all of those that seem to survive. I think it's table 11 at the end of the, or yeah, table 13. So table 13, after lots of regression modeling, you get that list of risk factors that seem to be independently contributing to explaining the risk of periapical health outcome. But it's something that is tailored to that particular population where the model was built. So I can almost promise you that when that model is applied to a different population, it's likely going to perform a little bit worse or substantially worse. Given the fact that it has been developed based on a large sample, there's some good hope it will not completely disintegrate, although it may even disintegrate. I mean, I cannot even promise that. But if I had to guess, I would say that it would perform a bit worse, and many of these factors that are included in the model will no longer be important in a different population where they would be tested. So the question that I have for you, why has this not been tested in a different population? I mean, is it that no such populations exist? Is it that the type of measurements that have been accumulated here are difficult for other centers to perform? They're specialized, or many of those seem to be pretty straightforward, but I was not sure.
Well, they had a very defined way of collecting their data, so all of these cases had exactly the same data collected, and that's very unusual in our field. Outside of this group is collecting a pretty similar set of data, but this was really the first time when a comprehensive set of data was collected that they could actually analyze all these variables. They measured all these variables when each of those cases was done. That typically is not done in our work.
So I think that this is a very, it's a considerable strength. I mean, if you manage to accumulate that information in detail. But I would argue that you would need to see that information collected also in other settings, and especially if it's not technically very difficult to do. Try to see whether that model could also predict what would happen to a different population in the US or Canada or Europe or wherever. How many of these variables, if you had different teams around the country or in your own practices, you would be able to codify with high inter-observer agreement? So if you had different people coding them and assessing the same patient, they would code them in the same way. And how many would be highly dependent on who is examining the patient and the tooth and collecting that information? What would you think?
That's very different. That would be where it would disintegrate, I think.
So, I mean, if I run through the list type of treatment, I mean, and you can tell me one at a time, type of treatment seems to be straightforward. Everybody would agree on how to code that and collect that information. Is that right? Periapical status, intact periodontal ligament, widened ligament, and periapical lesion. This is subjective. But I can buy subjectivity if there's no consistent pattern. Like, it's not that all the teams in the US would say that this is widened ligament and every team in Canada would say, no, this is just intact. Is there such a problem? It's just that there's a problem in assessing, but it's not a consistent...
Even intra-observer.
Even intra-observer. Okay. Yeah. Mm-hmm.
My guess is, and everybody here can correct me if I'm wrong, probably the yes or no would be easy, but how much would be the problem? For example, even yes 1 millimeter periodontal ligament widening, or 2 millimeters, 1.5. I think.
Right. Okay. But at least for these main categories of intact, widened, and periapical lesion, maybe there would be more agreement. I can understand that if we're talking about how exactly big the widening is, maybe there will be more disagreement. But at least for these big categories, maybe there's a bit more agreement. Then size of the lesion is, I think, what you mentioned. And I see that that would be a bit more noisy. Preoperative sinus, is it easy to tell whether there is or not? Okay. Pre or intraoperative perforation, easy to tell? Everybody would agree on that? Fairly? Patency at canal terminus? Yes and no? A bit more difficult to agree. Pretty easy, okay. Apical extent of instrumentation? Very noisy, not so noisy?
That whole chunk looks like moderately noisy stuff.
Uh-huh. Long root filling, how about that? Moderately noisy. Additional use of CHX as irrigant, you would know whether you used or not. So, and EDTA, you would know. And additional use, you would know. And inter-appointment pain or swelling, a little bit of subjectivity, maybe. Quality of restoration, at least for these three categories, satisfactory, marginal defect, and exposed root filling. Very subjective. So it seems to me that this is like a mix of some very subjective, some extremely objective, I mean, things like you did or did not, you know whether that happened or not, and others that are somewhere in the middle. Now, some of those are not just risk factors that belong to the presentation, but they are actually intervention related. So if you take, for example, additional use of CHX as irrigant, it says that if you do that, then the risk goes down to 0.47, p-value of 0.01. If I take that literally, it means that it decreases the risk of a bad outcome to about half. Just 0.47. It's a number that I'm reading just from the table. Don't have a. There's two screens, so I'm not sure that. But it's right there. Do you believe that? No. How many people believe that additional use of CHX as irrigant improves outcomes substantially? I mean, this is clear a big effect. You can cut the failure rate, however that is defined, to half. No way. Someone would believe that? So why is it there?
This is what we can't figure out.
Uh-huh. So apparently this is one example of some treatment effect that is expressed in a model of an observational study that is very difficult to say how much of that is confounding by indication. You know, people who had that procedure done, I don't know, maybe they had a more mild condition or mild disease. I'm just mumbling now. But
Blinded.
Yeah.
So it would not be blinded, could not be blinded.
Yeah.
So that would be a bias that we worked into that outcome. The researchers saying, well, I think this works better, so works harder on that particular case. I don't know.
Right, right.
Or failing.
Yeah.
Isn't this the same kind of, phenomenon that you just get with any randomness in a system? Where, you get enough people together, you're going to have some tall people. You might have an abnormally amount, you might have a basketball team in the room.
Mhm.
So now you've got a lot of tall people. But
Yeah.
when you look, isn't it dangerous to look at so many variables in a single, because
Mhm.
you're going to find some chance.
Yeah, absolutely. How many variables can you check? I mean, they have checked quite a lot. But they also have a large database. So, yeah.
It almost seems like they have the odds ratio backwards, because like they were saying that long root fillings improves your outcome, but they're saying that if long root filling is 0.38, that'd be saying it's better to have long root fillings. And perforations is being better than not having perforations.
Yeah.
Which is opposite of what's stated. And so it's like they have the odds ratio backwards.
So if you take, for example, the next one where EDTA seems to have a detrimental effect, do you believe this? No? Is it the opposite?
Yeah. Like in their conclusions, it states the exact opposite.
Well, let's see what the outcome is. You may be right. I mean, if the outcome is good, then having a smaller than 1 odds ratio, this means that it's less likely to be good. But whatever it is, do you believe these effect sizes? Not really. So what I want you to think about, and we can have a 10-minute break and then regroup to think about a design that would solve this type of problems. I mean, this is like, you're telling me one of the best studies. But you see some effects that are pretty large that at least in other medical fields we're not seeing that often. I mean, I showed you that usually we're dealing with 0.9s or 0.8s. Here, these are 0.47, 1.1, whatever they are. I'm so ignorant that I don't even know whether they're good or bad. But whatever they are, they're big. So the question is, how do we go after such big effects? And I want you to think about that for a 10-minute break and then regroup. But a question about this first.
What makes this a study prospective?
The fact that there's, that there's prospective collection of information and prospective follow-up, ideally. But is it so? So what is it? It's an observational study, yeah, but where the patients prospectively followed to see these outcomes.
But everything, if it goes from that direction, everything becomes prospective.
Yeah.
Misuse of prospective.
So it's an observational study. It has some strong effects. If they are translatable to an intervention, they would really make a difference. How do we go after them? Think about that for 10 minutes, and then we can regroup. There was a comment about whether the study was prospective or retrospective or what exactly had happened. There's a little bit of confusion in the literature about prospective and retrospective, because sometimes you may have a prospective cohort, but within that prospective cohort, you may have designs that operate as retrospective studies. For example, many nested case control studies operate as retrospective studies within a prospective cohort. Or sometimes you may have some additional analysis or outcomes that you're collecting, and then you're trying to associate with what were the features of the patients early on. And even though they come from a prospective cohort, they would be more like retrospective designs. But the study that I was showing you is, a traditional prospective study. So it's a very decent prospective study. I'm showing you another study that Gary shared with me, which I understand is also a very nice study and one of the best in the field. Is that right? This is a terrible study? Okay. Well, so this is a retrospective study. Okay, so in contrast to the other one done at Eastman, where people were enrolled and had their information collected as they were being enrolled, and then they were followed prospectively to see what happened to them. In that case, people asked, going backwards, patients who did have endodontic therapy 3 to 5 years previously, try to collect information, what had happened, and correlate their outcomes with how they had presented and what had happened to them. So a prospective study is a stronger design compared to a retrospective study. But as you see, even with the best intentions and I have no major reservations about the modeling per se. I think it's state of the art. At the end of the day, you end up with something that needs to be validated. You're not sure about how strong the effects are. Many of these effects that I showed you, you don't really believe that they would be that large in the final model. And some of these are potentially modifiable. So things that were done to the patients are modifiable, intervention-related effects. And in theory, if we could gain the same benefit as one would see based on the predictive model for the prospective uncontrolled study, that would be very nice, because we would be talking about changing the outcome twofold by doing or not doing something. But much of the time, it's not that we are selecting to use one irrigant or one type of treatment in a random fashion. People decide to do that because they feel that the case is more complicated, or it needs to be irrigated, or it needs to get that extra treatment because it's otherwise going to do worse. So it's very difficult to get rid of confounding of by indication, very difficult to get rid of channeling bias that we were discussing. And you could try to find some propensity score of variables in the presentation that are related to the use of different irrigants or different types of treatments. But even then, it's not going to be the perfect answer. As I mentioned, both propensity scores and instrumental variables to account for the imbalance of characteristics of people who get or do not get different interventions may help a little bit, but they will not give you the final answer. So if you want to have a more conclusive answer for these interventions or others, one would need to randomize participants to one or another intervention. And during the lunch break, there were some ideas that I was discussing with some of you about trying to use the consortium to run a number of randomized trials on questions that you think are very interesting. There's equipoise, meaning that we don't really know which is the best mode of action. There would be interest from participants to join and to allow themselves to be randomized to one and another action, and also have some follow-up that would be pretty complete, because otherwise you run into problems of non-response bias that we had been discussing earlier. For example, that cohort did have some non-response. Some people were lost to follow-up, but it was not a big problem, and it was not a big number. And I think for the range of follow-up, it was actually pretty good. But even modest loss to follow-up, if these people who are lost to follow-up have very different characteristics for those who are followed, could really invalidate the results, especially we're talking about effect sizes of relative risk of 0.8 or 0.85. They can easily be washed away by biases due to non-response or lack of follow-up or missing information. So what I would like to hear is some ideas about important questions where there's two different modes of action that you think we don't really know which one is the best. And Gary had mentioned one, but maybe you can give us the first discussion of that. We were discussing about a scenario where you do something or do not do something on someone who has a radiographic evidence of lucency and no symptoms and had endo in the past. Do I get it right? So the idea was, why not randomize these people to one arm that would get early treatment, intervention, and another one that would have deferred treatment. Deferred treatment does not mean that they would never be treated. You're unable to touch them ever, because sometime down the road maybe they develop something more, symptoms or worse problems. But at least when the randomization takes place, they're randomized to not do anything at this point. And several people around the table thought that that would probably work. that patients would probably be agreeable to be randomized to this. Some people may have second thoughts and change their minds, and after they're randomized, for example, to an intervention, maybe they decide they don't want it. This is still okay. This is part of a reality, real-life situation where it's impossible to have everybody adopt the procedure to which they're randomized. It's like a pill that in a drug trial, some people will take the right dose, other people will not take it, or will take some times, but not others, and others may even take double the dose by mistake or by intention. And we also said that there will be an operator component. So if about 100 different endodontists could join in that trial, there would be some randomization that would be stratified per practice. So whatever operator characteristics might differ would be handled at the level of randomization. So there would be a separate randomization log happening for each practice, and some of the people would be going to the early intervention arm, and others would go to the no intervention or deferred intervention. So this is one idea, and I'd like to hear what you think about this or about other ideas, about other interventions that could be studied in this way.
But then the randomization is based on the defects and not the disease. So it won't be relevant.
So what do you mean by defect? I'm not sure that I understand.
Asymptomatic,
yeah.
So we go with the size of the radiolucency.
So these would be asymptomatic people, and randomization would happen regardless of the size of the radiolucency.
No, I know, but it's like randomizing based on people having fever.
Yeah. Mm-hmm.
But we don't know what their problem is.
So you think that they should have some workup to identify some problems that may definitely need to be treated?
No, absolutely. I mean, that it has to be randomized based on what the diagnosis is. That's the big challenge in endo.
Mm-hmm. What do you do in these patients? I mean, if you see that, do you go down the path of trying to establish a diagnosis? Or do you leave it at that? I mean, if you leave it at that, I would argue if that's what you do, then that's what you should do. I mean, just randomize whether you intervene or do nothing. If you're telling me that all of these patients you would do some extra work and maybe arrive at a different diagnosis, then I would be willing to consider that as a prerequisite to whatever is done next. But I obviously, I have no clue what is being done.
I mean, that it's going to be a little bit like the same problem we have with heart disease. What heart disease is.
Correct. It would be managing people who don't yet have a myocardial infarction, but they have a high lipid levels or high Framingham risk score profile or some other risk factor that they are at risk. What we want to see, though, down the road is the outcome, and now I need your help. Which outcome one would need to choose? I would like to choose an outcome that would really be clinically important. That would be tooth loss or something serious happening. So that would be something that does matter. Even though the original observation is just a radiographic sign, the outcome should be something that matters. I wouldn't be happy if you tell me that the outcome will be just a change in the radiolucency a few months down the road.
Could you repeat that again? Could you repeat that again?
Why? Did I say something stupid? Or
No, it's something profound. I've been working on it for 10 years.
Okay, I didn't even know what I said. But I said that I would not be interested just in the radiolucency. I would be interested in something that clinically would matter as the outcome. But I have no problem to randomize people based on something that is, an asymptomatic sign.
So you're saying that measuring the outcome based on resolution of the periapical radiolucency is not a good outcome measure?
To me, but who am I? I don't know. I mean, if I could keep all my teeth healthy and I had tons of lucencies, I wouldn't care. Yeah, it would be nice. Probably I would be hanging it on the wall with all the lucencies.
To be honest, we make an inference when we have a finding on a radiograph, and that finding is what we categorize as abnormal. It's not normal. It's an abnormal finding. We make an inference that needs to be treated, and we are now starting to question whether that is a correct inference, because we don't know what happens to many of these teeth that are never treated. Does this finding get worse? Does it stay the same?
Yeah.
I think if you're randomizing people between, they have a lesion, they have a finding on a radiograph that's this size, so we treat it or not, and you want to measure the outcome of whether or not the patient became symptomatic, because all these are asymptomatic, whether or not the patient becomes symptomatic. If they get a toothache and end up losing a tooth or having it extracted or whatever, that's the outcome we want to prevent.
So symptoms, I'm willing to accept that this would be a useful outcome. I guess you have some way to standardize symptoms in terms of severity. So that would be very good to know. I think things like having a tooth extracted or lost, or I think that would be even more important to a patient. So I'm willing to consider different outcomes, but as I mentioned earlier, I think you're in a very happy position not to have too many outcomes, and hopefully we can arrive at one that would be the primary, maybe tooth loss, I don't know, and a couple of secondary rather than have dozens of outcomes.
Two other confounding factors. One is the outcome of our treatment, the outcome of the tooth itself may not have anything to do with the outcome of our treatment, because the manner in which the tooth, the condition the tooth presented in, or the condition, the way the tooth was restored later on may influence the fact that the tooth was lost, despite the fact that the quote-unquote microbiology got better. We don't know that. The other thing is, we are dealing with essentially a technique-based specialty, where our outcome is measured by the process that we perform. This study is attempting to take every surgeon, whoever did a root canal, and put them all into the same boat. And there are nuances, there are technique issues. The only, and this, I don't know, and maybe you can tell us, are we able to take all this work done by hundreds of operators and make a conglomerate of it? Because when you look at surgical studies, some surgeons have a better track record than others. We're all surgeons in this audience here. Some of us may have the same track record or different based upon technique and technique only. And there's only one study that I know of, which was done in the 50s, that had the same operator for 10 years looking at all of his work. And the analysis of that study may be flawed by monostatistical terms. But my bigger question to you, with these muddying factors, how do you conceive that we could control that? Because no one's going to ever be able to get a high sample size without taking several of us and putting us together.
This is actually an advantage. It's not a disadvantage. So this is a concern that always comes to the surface when you have an operator-dependent intervention, and where there's a learning curve, there's different quality of performance of the procedures, there's skill involved. But actually, I think that you have the ideal setting. I understand that you have a large team of very experienced endodontists with very good outcomes on average. So in a sense, you have the best shot at answering this type of question. If I were to take people who have no clue about how to handle this type of situation, I mean, I started becoming an endodontist myself, obviously, even the most effective interventions would fail in my hands, because I have no clue what to do. If you start having people who have some experience, you may see a little bit of the treatment effect of some effective interventions. If you have the best possible team of operators, then you have the best chances of revealing that there is a difference between acting immediately, for example, versus deferring, or perhaps it's better to defer, because when you defer and you wait for the right moment, then you have the best impact. I don't know. But this is really ideal, to have a large number of operators who can contribute. And the one thing that I would do is that I would stratify by endodontist, so that the protection of the randomization applies to each one of the participating endodontists. So if we do that, we avoid the situation where we would have 20 cases that come to Gary. All of them go to the early intervention, and 20 cases going to, let's say, to the least experienced member, going to the other arm, just because it happened to be so. whoever goes to Gary would be randomized to have equal chances to be on the early or deferred intervention. Whoever goes to the least experience would also be randomized to be equally likely to be on the early or deferred intervention. So if we do that, we can look at the overall effect. We can look at differences between operators. We can look at heterogeneity of effects across operators and whether this is beyond chance. I mean, there's more fancy secondary analysis that we can do, but in terms of the primary answer, you get an answer in a setting where you have tested it with some of the best and with a large number of them. So it's not something that only one could do. It's something that 100 different operators managed to get these results. So if someone could reach that level, probably the result would be generalizable. Yep.
I think the question here is, I don't think that the tooth that has not had previous treatment and has an apical finding, I don't think there's a question whether we should treat that or not. The question is, if the tooth has had previous treatment, regardless of the quality of that treatment, if now that tooth has an apical finding and they're asymptomatic, a group would be treated and a group would be not treated. My question to you is there a way to find the answer without doing a randomized control study? Because let's say the study starts. As soon as a tooth that is asymptomatic with an apical finding becomes symptomatic, that answers a question for us. Because that...
For the outcome of symptoms.
Exactly.
Yeah.
And remember that if the tooth has symptoms to begin with, we would retreat. I don't think there's anybody here that would watch the tooth that is symptomatic.
Yeah.
So if we knew there's 4 million, I think 4 million or 40,000 failing root canal treatments in a year that all endodontists across the United States see. If we see how many symptomatic failing cases we see, could we figure out the percentage of failed treatments that become symptomatic without actually studying? Can we collect data from patients that we see?
Yeah, I think you could do that. You could do that retrospectively or prospectively from now on, starting to collect that information. Much like the 2 studies that I showed you, one was prospective collection of information, the other was retrospective going backwards. But it's not really going to answer the question of what do you do if you have someone who had endo and now is asymptomatic and has some lucency. This is not going to be answered. You know, you won't be able to tell that it's better for that patient to be treated right now or wait until they become symptomatic or have some other problem down the road, and then it's the best time to do something for them. There's no way to answer that question in any other fashion. I mean, you cannot go back or even forward collecting information on what you do in a non-randomized fashion and be able to tell that it was okay that I waited or it was not a good idea that I waited.
I'm not sure that for even those who think waiting is okay, it's only okay for them, or me also, is if it never becomes symptomatic. If we knew for a fact, everybody in this room knew for a fact that every asymptomatic tooth with an apical finding becomes symptomatic at some time in the future, I think that we would retreat it. However, if we knew that maybe it may become symptomatic or maybe...
So let me give you one example. Let's say that we have that extreme, that you go backwards and you collect this data and you see that a very large number of teeth that were asymptomatic did become symptomatic down the road. Does this prove that doing something immediately at the point that they are asymptomatic is better than just waiting? I mean, it's possible that waiting led to those symptoms 5 or 10 or 20 years down the road, and maybe if you had intervened, who knows, maybe you would have lost more teeth in 5 or 10 years down the road. So it's impossible to tell just by looking at what happened to an observational series whether one or the other mode of action would have been the best.
However, when we do intervene and we see a response with either getting the lucency smaller or resolution, then doesn't that mean that we have improved the situation?
I would buy that if you think that radiolucency is what we call a perfect surrogate of the clinical outcome. And I know no medical discipline that has perfect surrogates of the clinical outcome. A perfect surrogate is not just a strong correlate of the outcome, which means a strong risk factor, it's also a strong correlate of the treatment response, which means that every single patient who has reduced radiolucency will do great. And every single patient who does not have reduced radiolucency will do bad. Do you have that? I mean, if you have that, then this is the first time that I see a perfect surrogate, and I can take it and say that then you have an answer. You don't need randomization. Instead of looking at other outcomes, you just look at radiolucency.
You also have the chance of not having any symptoms, doing a procedure, and then you have symptoms.
Because of the procedure, exactly. So I mean, so far we haven't discussed the possibility of the procedure causing problems on its own. So
you wouldn't know anything about that, would you?
Well, based on my personal experience, I had an endodontic procedure so that I wouldn't have a problem, and then I had a problem. My tooth broke within a couple of months, and you know, I had the non-problem for several years. Yeah.
Even though his radiolucency went away.
Oh yeah, it did.
So it is a surrogate for what you're saying.
However, sorry, I need to interject right at this moment before I ask him. How statistically significant would you give weight to what happened to you based on the 4 million endodontic treatments?
None. Absolutely none.
So really, I mean, that's one data point, which is really zero.
No doubt about that. I mean, you know, it was probably.
To your tooth, right?
It was probably not a good idea even to mention it, but there's. But there's just one. I mean, one example where you know things did not go according to the surrogate marker type of expectation. I mean, this is something that I think you need to decide as a group. If you think that you have very strong evidence of surrogacy for radiolucency or for whatever other tool might be available, then one might argue that maybe you don't need this type of trial. Now, if you read the methodological literature, to get strong evidence of surrogacy, you need two prerequisites. One, you need to have randomized evidence. So you cannot have a strong surrogate unless you have already run a randomized trial that had shown that what radiolucency evolution told us is exactly also what we saw in the clinical outcome. Number two, you need a large treatment effect. So you need a randomized trial that shows a large clinical benefit, and then you can take whatever candidate surrogate marker, map it along with that benefit and see that it does map and concord very nicely with the clinical benefit. In this case, there's no randomized trial, let alone treatment effect. So, you know, it would be completely a belief that, you know, radiolucency is such a great marker.
My question's a practical one about randomization. In a private practice setting, how do we ensure effective randomization when one intervention costs the patient a significant amount of money and the other intervention costs the patient practically no money?
Mm-hmm.
And you have to explain the study to the patient. Won't they all want to go into the group that costs them nothing? Or do we charge them, or do we not charge the intervention group?
Well, let me ask you.
If you're in an institutionalized situation, perhaps you can do that randomization fairly easily, where maybe you don't have a cost, or there's a much less cost. But say in a private practice situation, how do you do that?
So let me ask you a question, because again, this is something that I don't know. Of 100 such patients that you would see, asymptomatic with some radiolucency, how many of those, you discuss it with them, I guess, and how many of 100 say, I want this thing to be done immediately? How many say, no way, you're not touching this? And how many are somewhere in the middle where, you know, you discuss with them, you tell them more or less, again, let's discuss, and then, you know, and they may or may not have an intervention, but it's not that they're so clear-cut that they want to have the intervention. I mean, in my case, I was listening, you know, trying to decide, but you know, it was not that I felt that. So if there were a randomized trial, I would have liked to be randomized. But
if you're making the choice as to which group you're in, that's not randomized.
No, but you make the choice that you're not really certain, and therefore you're willing to be open to the possibility of randomization, and let's luck decide, you know, fortune or whatever you want to call it, and you have to explain. Since I'm not certain, you're not certain, we really don't know which is the best action, you can enter that study. You have a 50% chance that you may need to have something done right away, and 50% that we will wait until something else happens. How many people you think would be in that middle ground? Because if it's none, then it cannot be done. But I get a sense probably there would be quite a number. It's probably most of them.
We're all referral type practices, and the patient's coming in kind of ready to do what we recommend.
Yeah.
I mean, you would have to almost steer them into whichever it would be. You would present it in a certain light and say, okay, I think it's best that we don't treat this. I mean, relying on the patient to enter one arm or the other would be very difficult, as opposed to basically assigning them yourself.
Yeah.
In a random fashion, but
I think especially when there's a cost involved for the patient.
Well, the cost could be important in tilting some people away. So they may say, I don't want to run the risk of getting randomized with a 50% chance. But you know, I think there will be others who would be considering it, and it would not be an issue, and you will tell them, we really don't know which one is the best approach. There was someone that, like...
This brings up some ethical issues, too. For instance, if you have a patient that you have randomized in the no treatment group, and 2 years later they get an infection and end up in the hospital, and then they come back and say, well, how come you didn't treat me 2 years ago? And you say, well, you were this randomized study, you got me.
Yeah.
Their attorneys would love to hear that.
No, it's not.
Are you having make sure that the patients that are in this study would sign up for this?
Of course, yeah. I mean, the study needs to have an informed consent. I mean, people need to understand that they're having a 50% chance to be allocated to one or the other arm. And they understand that it's exactly because we don't know which one is the best course of action. Bad things could happen to them if they do get treated now. Bad things could happen to them if they don't get treated now. And this bad things will happen. I mean, you know, at a pretty substantial rate. If they don't happen at a substantial rate, then it's not a clinically important question. You know, we should seek something else. There would be several such patients that would have to be admitted to the hospital, but they should just be informed ahead of time. This is just the plain rule in any randomized trial, in any type of discipline. Yep.
The retreatment is not always a black and white scenario like we've been discussing, where there is a retreatment done and there is an asymptomatic periodic radiolucency. Many things we need to consider along with it as well. The quality of the first-time treatment. If there is an obvious canal missed there, then what would we do? Should we treat it or not? Yeah, that's even if it is asymptomatic, we should still treat it. We should not be waiting to see if that missed canal is good.
So here, it's up to you to define the exact eligibility criteria of what would be those asymptomatic cases with radiolucency that have something extra that you feel compelled that you need to act, and you don't want these people to be randomized. And this you can discuss. I'm not definitely going to be the one to suggest who those people should be. But my bet is that these are not going to be the majority of the patients that have something else that clearly is asking for immediate action. Yep.
So not sure how much background you have about this, but we're all here because 16 years ago, Gary tried to do this. He created TDO software for an outcome study. And they went so far as Gary and Rick. I'm not sure if do you know this?
Yeah.
Aware of it. So we could not get ourselves together for a randomized clinical trial. So it looks like that's off the table. What else would be nice, but it doesn't look that way. So what else should we be looking for? There's so much literature that comes across like this. What sort of studies should we either already have or should be looking for that we can draw some conclusions from? How can we get a randomized clinical trial?
What were the major obstacles for doing this?
The informed consent was a very difficult process. And so we had trouble with recruitment, and we didn't get the participation that we thought we were going to get. So there was a problem in getting enough patients. And I found because I had a prior that a 2-visit root canal was produced a better outcome than a 1. So the patient asked me, well, what do you think? And now I'm in a position to say, well, I really don't, I'm lying to the patient. Well, I don't know, that's why we're doing this study. So it put every clinician, whatever their prior belief was, whether it was 1 or 2 visit, in the uncomfortable position, because the patient almost always asks, what would you do if it was your tooth? So how do you answer that question? If your prior is, I mean, I'm absolutely convinced in my own practice that a 2-visit, a multi-visit canal.
That's not a question for a randomized trial then. I mean, if someone is convinced that one course of action is the best. So this is interesting. You know, obviously one has to revisit that strong belief, especially if there's strong beliefs on both sides of some people saying, yes, definitely 2 visits, and others saying, just no, definitely 1 visit.
But you wouldn't be doing this study, Gary, if you really knew the answer to that question.
Yeah, so it has to be a question that the majority of you, or at least those who would participate, would really feel honest that you don't know the answer. And again, it could be some who feel that they have the answer and they don't want to join in that particular trial. Let me put it in another way. You have about 200 members, is that right?
We have about 1,200 members.
1,200 members. Oh, okay. Wow. Amazing. So I was thinking not of just one randomized trial. I was thinking of dozens of randomized trials that you can perform. And literally disciplines in clinical medicine that took that paradigm shift step develop such agendas. And you have exactly the perfect background for that. You have a coalition of experts, of people who practice and see patients, and they're the best in the field, who could enroll patients into specific trials. And not everybody participated in every trial. So if you think of 12 questions about things that some of you feel strongly about doing, others feel strongly about not doing or doing it differently, and there's several who are in the middle ground, then for trial number 1, it could be 200 out of the 1,200 endodontists who participate. For another trial, it could be 50, and they could be unrelated to the 200. For a third one, it could be another 100. So you need the people who can really be honest to themselves and to their patients when they say, I really don't know which is best. The ones who think for a particular question that, no, I know really what is best and I cannot be dishonest to my own self, those should not participate in that particular trial, but they can participate in something else.
I don't have any problem with saying I don't know, but I have a problem with, which is a different question that the patient is asking, is what would you do if it were your tooth? That's a different kind of question.
But I think what he's saying is that you want people doing the trial that can honestly answer, I don't know what I would do, because I don't have enough confidence in either answer to give an answer that I would that I know. And so those are so you have your people that are convinced one way or another and said, I would do this or I wouldn't do that. Those you don't want. You want the people in the middle that say, I don't know what I would do.
But
That's why
honestly,
we're doing the study.
Yeah. And I think that it would be possible to find a sufficient number of endodontists who are in that middle ground and could honestly say, I really don't have a strong preference on what to suggest to you. I mean, we were talking about some back of the envelope sample size calculations, but for substantial treatment effects, because this is really what we are after, and for common things, and these are common things, so I think we're talking about 50% failure rate. So if you want to show a 50 to 25% risk reduction, you only need a few hundred participants, which means that if you have 100 endodontists participating and each one of them could enroll 4 or 5 patients, this is more than plenty to run a trial of that type and have a definitive answer after a couple of years. So to me, it seems like a win-win situation. You have built that infrastructure. It is in place. You have some interesting questions. You have debate, clearly. It's not that you agree that that's exactly what needs to be done. No doubt about it. This is the ideal situation to run these types of studies. Yep.
With regards to numbers and having lots of endodontists participate, is there a difference if you have 100 endodontists in one case or one endodontist to 100 cases? Does that make statistical?
It's not such a big difference, no. I think that there could be some minute issues with the stratification or with blocking of the randomization, for example, depending on how uneven the distribution is. And obviously, if you have a situation where you have one endodontist having the predominant practice and running 300 cases and everybody else, 50 people get another 50 cases, clearly the results will reflect what happens to that major practice. But is that good? Is it bad? It tends to erode a little bit of the generalizability of the results, because then it's only one practice that dominates the results. But I can live with that. I mean, we're talking about like small details compared to the big question and to the robustness of the design that randomization could offer in addressing these questions.
So if everyone offered, say, 4 cases,
yeah,
2 of which were real.
Exactly, yeah. So that would be perfectly fine. I mean, if each of you could enroll 4 patients, I think that would be ideal. And I think it shouldn't be that difficult to find 4 patients. Yeah.
Well, going back to about the radiolucent finding that you see, I see one of the problems is that in dental school, they're taught, that you see a radiolucency and abnormal finding, and something should be done. And even our own parent organization would probably tend to go that route too. And so you got this push about, okay, something should be done in that situation, as opposed to, us, which is a think tank that, we're thinking maybe this is not right, or maybe there's, things that we need to really consider before, pushing the button on doing kind of treatment. And then the other factor is also that we're not primary care dentists. And so these patients we may just let them go, and then, either it could blow or it may not blow. But let's say, our periodontal colleagues, periodontists, they see this and they say, oh, you have pathology here. Something's got to be done. Let's take the tooth out. And so you have that too to deal with.
So lots of things could happen.
Yeah, so we're really subcontractors. I think that's the way I look at us as endodontists. We're subcontractors. We're not primary care people, and so a lot of things are out of our hands, and then patients end up losing teeth too. So.
But this is perfectly fine, and actually I would say that it's even advantageous, because if you were in a situation where you could even manipulate exactly what would happen, let me make it extreme. Let's say that some of you participated in the trial and felt very strongly that late intervention was the way to go. No, not intervene now and just let things happen. I'm making it too extreme now, okay? I'm not saying that this is what's going to happen. So I want to prove that late intervention is the best thing. So I want to show that early intervention is bad. And what is the outcome? Tooth loss. Okay, so here's a patient who was randomized to early intervention. I see a minor problem. Take it out. Remove that tooth immediately. And then you count outcome, tooth lost. So the fact that you don't have that everyday control on what's happening to the patient is not necessarily a bad thing. It's actually a good thing. You want to remove yourself from the intervention rather than chaperone it all along and everything possible to show that one or the other theory is correct or wrong. Now, the component about an organization taking a stance or medical school and dental school knowledge, I mean, we've seen that again and again and again. I mean, textbook knowledge, there's classic papers that shows that it's completely unreliable. Guidelines are up for grabs most of the time. There's plenty of evidence that very well-established medical interventions, when we do test them in randomized trials, about 50% of the time they fail. So ethically, scientifically, on all aspects, this is perfectly fine. It's really entirely legitimate to do it. Yeah?
I'd like to help answer Fred's question. Fred, the purpose of the clinical trial is to inform the decision for what your strategy is for treating the patient. Part of the outcome of the no treatment strategy is the periodontist sees the case, sees a lesion, and yanks the tooth. That's part of the real outcome of that strategy. You have to incorporate that might happen.
No, I realize that.
Okay.
I just excited to have that word in a unique situation that we're really not primary care.
Yeah, no, this is ideal. I mean, in most medical trials, we're trying to make sure that those who apply the intervention are removed from the rest of the care of the patient, because you want to have the person who intervenes and the person who assesses and the person who sees the patient to be completely different, ideally completely different. So my problem, if anything, is that you still have some connectivity to the periodontist or whoever else, and some community, and I'm not saying not communicate with them, but this is okay. This is perfectly fine. Yep.
I think it's really important for a basic and fundamental question that we should be asking us, and that is, if there's a patient who has had, who is symptomatic, yes, and has a periapical finding, what is the goal of our treatment? And shouldn't we be going towards that goal? For example, is it okay if a patient has a symptomatic tooth with an apical finding, with a failing root canal treatment? Is it okay to get that patient out of pain by doing the retreatment, but to leave the finding the same, or have it enlarged? Is that a goal? Would anybody say that that's a goal for their treatment? If our goal is to reduce or get rid of the apical finding and get rid of the symptoms. Now, with the symptom not being there, should reducing the lucency be also a goal? Are they mutual?
You have come up with an excellent, different randomized trial. So this is a different population now. These are symptomatic patients. I mean, we were talking about asymptomatic patients. Now, this is symptomatic patients. And you have two strategies that you want to randomize to. One is symptomatic relief. The other is symptomatic and radiographic, or as you may want to call it, improvement or resolution. And you can randomize patients to these two strategies and see what happens down the road and who have the best outcomes. And this is yet another randomized trial that some people would say that I'm not sure whether I would only try to relieve symptoms or also do more than that. If there's people who have that ambivalence and are at equipoise about this, they should participate in this study.
But it's a consequence of our intervention that although we get rid of their symptoms, we also reduce or heal the lucency.
Sure.
You can't have one without the other. It seems when there is intervention, not when there is an intervention, when there is intervention.
But here, again, I'm not
Nisha, what do you mean you can't have one without the other? We have one without the other all the time? What are you talking about?
You have
We have a
treatment.
symptomatic teeth that you retreat, and you retreat it, the symptoms go away, but the radiolucency stays there. That happens all the time.
And what is the percentage, would you say, from your experience or from all of our cases?
When you start taking cone beams on your patient, you'll find that that percentage will go up.
Strindberg already
A lot.
published that.
Again, I don't know how common these constellations or combinations of radiographic and symptomatic relief and resolution are. But if you don't know, then I would argue that this is a very good question, I mean, to address. But yeah, there were people, I think I have moved a lot on that side.
I have two questions for you.
Yeah.
First one, was a specialist who provided treatment in your students?
Who was?
Was a specialist who provided your
Yeah.
treatment with a microscope.
Yeah.
So,
What was his name?
So far, because I understand even being in this selected group, we're gonna have different approach. Like Dr. Carr stated before, he believed to be less aggressive, to keep the root minimum, flare, and use the medication to disinfect the tooth. So if we go one visit, we might need to flare a little more, go a larger size of the enlargement of the root to provide this better sanification of this system, canal system. So those different approach and different specialists is a big variable that cannot be put together in one only study outcome or randomized clinical trial.
Well, if you think that you cannot put people together, then you have just described yet another randomized trial that needs to be done. And unless everybody agrees that you cannot put people together who had this type of microscope or widening or whatever. I'm mumbling now in terms of terminology. But really, I'm coming back to the two trials that we described. One is asymptomatic people, and you do something, whatever you feel is best, or don't do anything. You have experienced people who probably do their best. I mean, I can't believe that anyone will do something suboptimal knowingly. So some people will use different approaches, different techniques, different tools, different microscopes, different whatever. That's okay. This is part of reality. This is life. This is what you do all the time. I mean, and you're happy with that. I mean, it's not that you cast someone away or out because they're using this microscope and they shouldn't be using it. Is it so? Or if there is such a practice that you think should be outcast, you should define it in the eligibility criteria. It should be in the eligibility criteria that acceptable practices include A, B, C, D, E, F. And those should be things that people should think that they are okay. You wouldn't say that that was a mistreated patient if that was what was done. Now, if you have uncertainty whether a microscope should be used or in what type of microscope or what type of approach or what type of widening, and there's really a lot of ambivalence and equipoise, again, this is another topic for a randomized trial. And these trials could be run at the same time. What I'm describing to you is a full research agenda that could have 1, 2, 10, 20, 30 randomized trials running at the same time. For whatever questions, each one of you has equipoise. You may create a list of 10 questions, and Gary would say, for these 3, I'm not going to participate because I have strong feelings, strong beliefs. That's always what I do. That's always what I tell my patient. I'm not going to be able to tell my patient that I don't know what to recommend. There will be 3 for Gary that he would like to join in a randomization. Yes. Well, let me clarify that. If you design the whole process as a single factorial trial where people could be randomized to multiple types of interventions or not interventions, then you don't need multiple IRBs. It will be one trial. So, for example, if in the symptomatic setting you have 3 questions that you want to ask, I don't know what these would be, but if there's 3 questions, you can randomize patients to each one of these 3 at the same time. So this is a a 2 by 3 factorial design, it's a single trial practically, but you answer 3 questions. So it's 3 in the price of 1, including the price of IRB ordeal. So it's not a big deal to get this through.
You know, another random question about randomization.
Yeah.
So you're saying, I want to make sure I have it right, that there can't, without equipoise, then randomization is not possible, a randomized clinical study.
Yeah. Mm-hmm.
So if we were all in this room to say, we're going to take our next 20 patients, regardless of our priors, we're going to randomize the treatment on them. That is not effective. It's possible, I know, but is it useful?
Randomized to which options?
Let's say we're investigating one small area, 1 versus 2 visit treatment. And we've all got our own priors about whether it's 1 versus 2 versus 3 versus multi-visit. But for those 20 patients, and by the way, 1 versus 2 versus 3 versus multi-visit are all accepted treatments. It's not like these are below any kind of, there's no clinical standard, there's no clinical standard of care that's certainly been published by these our parent organizations. So now, although I've got priors, I'm going to take my next 20 patients and I'm going to randomize whether I do 1 or 2 visit root canals on them, even though I already have a built-in bias. Is that, I know it's possible to do, is from an experimental or analytical standpoint, can that be analyzed properly, or is it, because there's no equipoise, is it useless?
Why is there no equipoise? I understand that you're not really sure on whether that's...
We've already, unfortunately, everybody in this room is sure about what we do.
Okay. But not everybody is sure about exactly the same thing that needs to be done. Yeah. So that means that there is equipoise. It means unless it's only, you know, a couple of weird people who do one thing and 198 on the other side.
But choosing the 1 versus multi-visit approach,
Right.
okay,
Yeah.
that's just limited to that. If you go through the room, there are some that will do 1 visit, most may do multi-visit. But now we're going to form a group. We're not going to go through an IRB, okay, because both treatments.
Are we doing all of that to avoid the IRB? Or no? I mean,
There consents or consents. We all have people sign consents, no matter, you know, when they look for treatment. So there's a consent for treatment, and it doesn't really matter because these are all clinically acceptable procedures. Whether it goes one or 2 multi-visit, we're just interested in the outcome for our own purposes, and we're willing of those 20 patients to handle any unfortunate outcomes, and just between you and me and the lamppost, maybe we won't charge these patients for any bad outcome.
I think that you know, we are entering a discussion about how to make things more easy administratively rather than, because I think that, you know, the IRB issue, if you're set up as a consortium of investigators who want to address a scientific question, I mean, there can be legitimate ways that one could have that approved probably at one place rather than have like 100 endodontists, each one of them apply and get approved. It becomes a multi-center trial that could have streamlining in the approval process. It should be very straightforward to do. We just need to find the exact place to go for that. But that would not be the rate limiting step. I don't want to see that as the rate limiting step. The rate limiting step is willingness of sufficient people in this room or others related to the coalition to enroll patients for one or another research question. And if there's willingness to do that, the rest, we're talking about 20,000 randomized trials done every year and about 1 million that have been done until now. So we're not going to do something that has never happened before.
You know, the study is not done at university, so why there is a need for IRB?
We can check the exact details. I mean, yeah, it needs...
There is no need for IRB, but you need informed consent.
You definitely need informed consent. I think that we could check the exact qualifications to make sure that we are okay and, you know, ethically we're doing the right thing. My belief is that there should be some review by an independent body Right? So this would be IRB. You know, it's an independent body. It doesn't have to be like every single person being reviewed by a different independent body. I mean, that would be completely crazy. But there are such processes that are very simplified, and you can have that done. I wouldn't stick to this. This is doable. This is what people do all the time. The important issue is to arrive at what are these scientific questions that are more ambivalent and more likely to attract more attention among the members of the coalition. And they would be feeling honest to themselves and to their patients to enroll participants in these studies. Yes?
Well, I have two questions. First off, who is the coalition? Who runs the coalition? What's its governing body? What's the organization of it? I think there's some obvious answers to that. One of them is sitting over in that corner of the room. And the other comment is that there are questions that I think we'd like to have answered that I don't think require necessarily randomized studies. It could be observational on the data that we've already got. Because this is pretty robust software. The other thing, we're now transitioning from two-dimensional X-rays into cone beam CT, three-dimensional X-rays. And there's a lot of questions around the diagnostic ability of those. I think those questions could be looked at without randomizing studies. So I think if you're going to do this, you want to define, as you said, 10, 20, 30 random studies, but on top of that, you can have some observational studies too. So you need some kind of organization.
I don't think that one excludes the other. So, I mean, you have that database in theory. You could start looking at observational questions any moment now. I don't know how much data has been accumulated and what is in there. I'm not saying this is not interesting, and I'm sure there will be lots of interesting questions that you could try to approach based on just the observational collection of information. But to me, really understanding treatment effects of treatment choices is really going to raise the level of evidence in the field. It's a transformative step, in a sense. Maybe I'm a little biased, but I don't think that much. Yes?
One of the problems that I have with a randomized study is that you want to have certain teeth you're going to do in one visit and certain teeth you're going to do in two visits. But I find it's hard to do a tooth in one visit anymore. I mean, just physically, and trying to do a molar, let's say, that's what, I think we all are more interested in, these complex teeth like molar. I can't do it in one visit, just physically anymore. I guess, I don't know, maybe I'm older now and I get tired talking.
So, I think that maybe this is what you believe, and maybe this is something that everybody in the room believes. If this is something that everybody in the room believes, you should not run a trial for that particular type of clinical setting. Right. So I'm not telling you to force yourself. I'm telling you, try to think about what type of clinical scenario you would feel comfortable to have the option of randomization. Maybe for a molar you wouldn't do it, but for another type you would do it. Or then you have to define what would be the eligibility criteria. And again, it doesn't have to be that everybody in the room participates in every single trial. It would have to be those trials that seem attractive and with sufficient equipoise for the particular endodontist to participate.
You said a few patients per practitioner. How do you decide about the number?
I don't care how many patients are recruited per participant. I care about the total number. So the total number we have to agree ahead of time based on sample size calculations on what is the effect size that you want to have 80% power to detect if it's there so that you don't miss it. How you recruit those patients, so if we make these calculations, we say we need 300 patients. As I said, it's okay if you have one who recruits 100 and others who recruit a few. It's okay if everybody recruits 5 to 10 or 3 or 4. That's not an issue.
Okay, if like one practitioner has like 3 or 4, which technique they are going to use to randomize the patients?
The same that would apply to everybody. This is like tossing a coin. And here comes a new patient, you're tossing a coin, and heads or tails. Yeah, but it's not a coin. It's a computer code. But otherwise, it behaves like a coin, though, like a fair coin. Yes.
Let's say this never comes about. Everyone just doesn't get it going. If we want to answer that question the best way retrospectively, I have some skepticism if this would be able to go forward, but it's a great question that I never thought of until somebody came visit at our school a couple of years ago. What would be the best way retrospectively to look at that? Would you see teeth that came in that had a radiolucency that have no symptoms, and then try to go back and look how far you could and see if they went, or is there a way you could ever do that? Because I think you could help us design a study where we could do a prospective study, but to actually get it done, and I hope I'm not too much of a naysayer here, but to actually get it done, I'm skeptical if we would.
Well, retrospectively, you can even go to the database that you have now and try to see how it looks like. But the credibility of that information is going to be very tenuous because what people have done or not done depends on how the patient presented, what they thought was best, how severe the case. I mean, I'm not an expert in the field by any means, but I'm confident that it will be confounded by indication. I cannot think that it would not. So it's going to be a suboptimal answer. It's something that you can probably obtain by the end of the day if the data has been accumulated already in the software. But it's almost going to be like equally likely to be wrong or correct. Actually, there's many ways that an answer can be wrong, so it's more likely to be wrong one way or another. So I don't know, maybe I'm applying too much pressure, but I think that you have a very unique opportunity here. I've talked to many groups of very different specialties. Most of the time, the most difficult step is to get together. So this is what doesn't happen. And in most surgical specialties, this is almost an insurmountable obstacle. Because, I don't know, many surgeons believe that they are the only one on planet Earth and they cannot sit on the same table with someone else because their skills will deteriorate. So you have gone through that step and you have that coalition in place. And you have this wonderful environment to exchange information. And I think that the next steps are really things that have happened a million times, and we know how they can be done, and the resources are there. It's not so difficult. The questions seem to attract enough scientific debate already, even within 1 hour, that we have been discussing them. This is a very good sign. If everybody said, oh, well, yeah, but I heard people who fight against some of these ideas, and others were very favorable to them being tested. So I would think you should definitely go for that. Yeah. Thank you.